only way is to claim that the solutions to these equations actually give information about non-perturbative effects in these theories. And moreover, so that's the equations themselves are very well known. They are generalizations of some equation. Well, in the simplest case, they were invented more than 100 years ago, and quite funny, invented by a prime minister. So, which is especially funny. But anyhow, that's what we have. And even the derivation of what I'm going to say is also very tricky. You actually, in order to derive them, and if we have time, obviously then that we do not, you have to lift to 5D and consider instead of 4-dimensional, 5-dimensional gauge theory with a single compact dimension, and then it becomes so related to some discrete flows and discrete equations, and so that's the only way known up to now. And so this is actually a sketch of some works with these young people who are listed here. Two of them are, last one are my PhD students. Pasha Gavrilenko was my PhD student, and Misha Bernstein have never been my student. Okay, so that's about 4D and equal to supersymmetric Young-Mills theory. The action is written here. So actually these are the bosonic fields, all in the joint representation of the gauge group, plus some fermions, which are an essential and classical solutions, plus the topological term. And so it is, that's old story. It's very well known that Higgs condensate, here this adjoint Higgs, breaks gauge group up to abelian in general position. This is called the Coulomb branch. And the theory of this Coulomb branch is described by gauge invariant parameters. In SU2 case, this is, for example, just trace of phi square, generally the coefficients of characteristic polynomial. And the aim of all that, what I'm saying about the sector, not only particular theory, but particular sector of the theory, is to describe this effective U1 rank gauge group abelian theory in the infrared. So infrared is very essential. So all words here, I try to reduce their numbers, but all of them are very essential. So again, that is very well known, old story. And about loop effect, so here for renormalization of coupling, so this is actually just exact one loop renormalization group formula when applied to this different quantity. So it's dependent of the actually infrared coupling of this condensate parameter. Here is the positive or at least zero coefficient of the beta function. After all, at the end, hopefully, if I do not have time to pronounce these words, I pronounce them now. This way gives, well, some steps towards ultraviolet completion, towards understanding of the ultraviolet completion of these theories. So this is actually some picture. Here it's log E just to demonstrate that basically this is the same formula as the formula from renormalization group, where in n equal to this is just a straight line. And actually in abelian theory, this is a horizontal line because nothing is renormalized. And what is important in n equal 2 is first that there is a natural complexification. And as usual, life becomes simple when you have some complexification and holomorphic dependence. So you can unify these two parameters into a single complex coupling, which depends now holomorphically on U. And all that perfectly works at weak coupling, where modulus of U is much bigger than lambda squared. Actually, both these constants can be also complexified. That's why I forgot about modulus. And naive prediction, if you just consider perturbation theory, is that at U equals to 0, non-abelian symmetry restores. So, well, we can say that we know, though it's not an experimental evidence, but it's an evidence checked by many checks through 20 years, that it never happens. So an obvious abstraction is that this formula, perturbative formula, does not work at modulus U less than lambda square, because you have contradiction, this coupling becomes negative. And instead, there is non-perturbative corrections to these formulas, which totally break the whole picture. So pictorially, at u equals to 0, there is no such point. I mean, it's not distinguished by anything. Instead, there are two singularities with in this modulus plane with massless monopole and dion. And actually, in the vicinity of these points, or just in the whole region, theory is described by electromagnetic dual theory, which is essentially abelian, so which has no non-abelian relative. And the question, so what we can say about this theory is, well, there are certain particular observables, or I mean parameters which we can compute exactly. And these are in particular the couplings in the effective Lagrangian, both in the original theory in weak coupling and in the dual theory at strong coupling. And n equal to special Kähler geometry says that they are expressed through a holomorphic function, through a single holomorphic function. And one of the aims is to find this function. So what is known about it? So it's called prepotential. It's known, and originally it was known from some physical reasoning, that it has some particular expansion at a goes to infinity. So the first term corresponds to this logarithmic one-loop contribution. And moreover, then there is a tail in powers of lambda over a. Here, essential is that here is a coefficient 4, which is a beta function of this n equal to supersymmetric H theory. And this expansion looks like an expansion over instantons. And so finally, well, there is this story related with integrable system and its deautonomization, which allows to compute the coefficients of this expansion. And indeed, it was later found that these coefficients indeed have instantonic interpretation.
What is deautonomization?
It means when you take some integrable system and then consider its parameters being time dependent. Okay? I will say in a couple of words, in a couple of slides.
You will,
Yes, I will show. Sure. And at strong coupling, this dual prepotential which describes theory at strong coupling, it has very similar actually expansion, which but its expansion here in monopole point at AD goes to 0. And the point is that powers here are different. No instantons in abelian magnetic theory, no coefficient 4, and no way to compute these coefficients in contrast to Fk from some original reasoning, except for writing some sort of some differential equation coming, so as Andrei asked, from the deautonomization of an integrable system. So where integrable system comes from, again, it's an old story. I will briefly skip it, because just the statement is that this formula, yeah, can be completed if you just say that the set of couplings is given by period matrix of a Riemann surface. And the first hint is that any Riemann surface obeys some group of first homology, and the basis of cycles in this group of first homology reminds strongly the electric and magnetic charges in supersymmetric gauge theory. And second point is that imaginary part of this period matrix, this is a natural object on any Riemann surface, it's positive definite, so it never goes to be less than 0, contradicting to the physical property. Under degeneration, it has a logarithmic behavior, and so it's actually a nice candidate for the set of effective couplings. And a simple statement about integrable system, let me skip all these details, that indeed there are certain period coordinates which can be identified with the masses of the BPS last BPS states. And in these coordinates, this period matrix is indeed a second derivative of a single holomorphic function. So the whole integrability here, or just Riemann bilinear identity, says that these conditions are actually integrable, that you can express many variables in terms of a single function. And the answer to this question, again, it was known long ago, that for, say, pure n equal to supersymmetric gauge theory, when you have just a single n equal to vector multiplet, this integrable system is a very well-known Toda chain. So the equation of for Riemann surface or complex curve is given by these formulas. It's endowed with these two pair of differentials, whatever, and you can easily derive all these formulas. And the question is, as I said, does F satisfy any reasonable, maybe integrable or other equation? So, well, how to look for it? So now it's already more complicated. Instead of oversimplified, very simple example, if gauge group is U1, then this equation is very simple. It's equation of a rational curve. Everything is computed, and you can find that F is actually given by an explicit formula, and it satisfies this equation. And this is, if you look carefully at this equation, it's an equation for a Toda chain. So it's an integrable system, very well known, appearing everywhere, just in any, almost in any issue. And F is called the logarithm of tau function of Toda. And this is just an equation for this logarithm of tau function in this long wave limit. Generally, here you have a discrete derivative. So instead of this equation in the oversimplified example, what do we have? So we have first non-autonomous version of Toda. We have to take some sort of epsilon deformed theory. So we actually have to deform a background where our supersymmetric gauge theory live in order to ensure at least the infrared regularization. And then naively, one would say that this is the object for which one have to write down an equation is just some deformed tau function. Yeah, I wrote it down in such a way, but actually it's a Fourier transform, and an equation would be written for this particular object. H bar is the same as epsilon. I'm sorry for this misleading notations. It has nothing to do with H bar of four-dimensional gauge theory. And again, to derive, we have to go up to 5D. Now, an answer to the question of Professor Smelga. So what is deautonomization? Instead of Toda, you have sine Gordon with a coupling which depends on time. You see, right? Tau is time here, and tau is the same as here. Here is just the same as radial sine Gordon, or the simplest case of this Pine-Levé-3 equation. And so that is goes back to 100 years ago, and actually to use Andrei Prime Minister. As I understand, Mathieu is a Schrödinger equation with such potential. But as I know, if I'm correct in terminology, but here it's just a classical equation, classical differential equation.
If you would have not hyperbolic sign, but ordinary sign, then, and if the constant wouldn't be time dependent, that would be just usual, well, physical pendulum, right?
No, it's not physical pendulum. At physical pendulum, this coupling is fixed.
Yes, I understand. So it's
but if it is time dependent, yes. So here which slice doesn't matter because everything is in fact complex, and you should carefully treat different real slices. But what is important that this coupling is time dependent. Okay. So that's why this equation is not solved in terms of theta functions. Like physical pendulum is solved in terms of theta function on an elliptic curve. For this, nothing. And so then I can, so this is what is called deautonomization, and generally instead of isospectral problem, you have to consider some isomonodromic problem. But here also, everything becomes far more complicated, but still here you can introduce these tau functions like in integrable case, and the question is about the properties of these tau functions. So what we have for tau functions? So this is actually the statement. The tau function, which satisfies this non-atomos differential equation, can be, I said about Legendre Fourier transformed, it can be Fourier transformed And the coefficients of Fourier transformations are these blocks which are written here. These blocks have some at t goes to 0. This is expansion over positive powers of t. So these are fractional actually powers, and the expansion of this object in t is over ordinary integer powers. And they have some clear, well, maybe not very clear, but definite sense in the deformed SU2 gauge theory. So first of all, this t is just lambda 4. So expansion is over expansion of this coupling, which becomes dimensional in this pure gauge theory due to dimensional transmutation. So A and eta are at the moment here just two independent integration constant, because Pan-Levé equation is a second order differential equation, and its solution is determined by two integration constants. So this first term is just a classical part of a classical prepotential. Now, these Barnes functions, which appear in this formula, they correspond to loop effects, to one loop contributions. The most easy way to see this, it's not so easy to explain in full detail, but at A goes to infinity, it's like Stirling formula. This Barnes function has this asymptotic, and A square log A is this one loop term in the prepotential. And finally, the most tricky part is this B. So this can be defined, here should be comma, as a sum over here in SU2 case over two partitions, lambda and mu are two partitions. So in integer power of t, so the sum of the squares in both Young diagrams is the instanton charge, and the coefficients are some rational functions of these masses. Masses are given in this theory by a single parameter for condensate, and these are called Nekrasov instanton partition functions, and they indeed can be derived and were derived not in an easy way from instanton calculus. So that's about these functions. And so what we can say more, so, well, simple things. Equation is known for 100 years, as I said. The analytic properties of the solutions to the Pan-Levé equations already contain some important information about non-perturbative super-Young mills. So we saw this formula for the tau function. So this t lambda square gives you beta function. And for example, expansion at t going to infinity, like in supersymmetric gauge theory, goes in fractional powers of t or in lambda or inverse powers of lambda without this coefficient 4. So this is just a hint that this is the same what we should expect from non-abelian or abelian theory expansions. Now equation. This is this non-autonomous Toda equation. It looks very similar to this formula, a part of, again, this fact. So what is non-autonomous? That coefficients of these equations explicitly depend on the time variable. And moreover, the studying of the solutions to these equations, singularities of the solutions allow you to obtain some important information like this. I won't say even what is it, the Nakajima-Yoshioka blow-up equations, which relate instanton partition function in different backgrounds. Okay, so thank you. Let me maybe skip some details and finish. So I will just say a couple of words about 5D. So, well, it's very strange, but this 5D appears to be more powerful than 4D in this setup. What is 5D? As I said, is a theory on R4 cross some circumference of some finite radius. And already, well, what it means physically, perturbatively, it's very clear. If you remember the story, how I tried to say that the period matrix is related with the complexified coupling, you can compute the period matrix here in the degenerate case. Here it's even written how to do this. And this integral, which gives you period matrix, it's logarithm of sinus of A. So it's actually, instead of just logarithm of A in four-dimensional case. So this sign collects contributions from all Kaluza-Klein descendants over this compact 5 dimensions. And one of the reasons why five-dimensional theory works better is that actually five-dimensional Nekrasov functions, they appear from study of quantum mechanics, some finite dimensional quantum mechanics on the instant modular space of instantons. So this circumference plays the role of a compact time in this quantum mechanics. Not an explanation, but the only hint is now. And so now I will just show you a couple of pictures. So these integrable systems in 5D can be written as integrable systems on cluster varieties. It's a very, they are encoded by some funny pictures. I won't explain you the details. So the phase space is obeyed with some logarithmically constant Poisson bracket, whatever. And so this is the picture which allows to study these theories very effectively. So this is so-called SU2 Toda quiver. So quiver is just a set of vertices with arrows which encode the Poisson bracket. And I want to show you how this deautonomization easily shows up in this case. And maybe one of the reasons is that it's very hard to do in 4 dimensions, but it's very easy to do this. And we have to recollect one great scientist from Dubna, who is not already with us. It's Alesha Zamolodchikov, who actually first started to study these problems in relation with thermodynamical Bethe ansatz. So what you have to find first? First, you have to find some integrability, some transformation where the Hamiltonian is preserved. How it's done here. Here, there's a sequence of discrete transformations which are called mutations, which are Poisson transformation. And what, again, found by Alesha long ago, the story is that you can mutate this quiver, so make the transformation of the picture and of the variables. And this, after the sequence of mutations, you can, for example, delete these opposite arrows and come back to a picture which is similar to original one, actually up to a permutation. After permutation, it becomes literally the original one, but the variables are transformed. So this is the symmetry. And so what I can say about this symmetry? This Poisson manifold has 2 Casimir functions. So functions which whose Poisson bracket is 0 with any variable. One of them is distinguished, is the product of all 4, and another one is the product of opposite, here playing the role of gauge coupling. And so you just write down an equation of this simple algebraic transformation for the variables. You see that when written in terms of these functions, z is multiplied by q and q remains intact, whether it's 1 or not. If it is just 1, this is the set of transformation which preserves the Hamiltonian. So it's a discrete integrable flow. If it's not 1, what happens? Then you consider it as a discrete time. And after some redefinition, you see that x's can be considered now as functions of z, and this function satisfies second order difference equation, which is just this Q Penlever 3. That's it. So now you can rewrite it in terms of tau functions, find all these formulas, etc., etc. And I would like to finish with some of these pictures, for example, with this one. This is the set of quivers in this Penlever case. So this one corresponds to pure gauge theory. This one corresponds to the pure gauge theory with 5-dimensional Chern-Simons term added. And I remember how long ago Fok, Nekrasov, Rosler, and Selivanov were studying this in ITAF, starting to study this in ITAF, and nevertheless it's come out here. So this is a theory with a single hypermultiplet, with 2 hypermultiplets, with 3 and with 4. But in 5-dimensional case, this line can be prolonged. And probably that's, well, should be the same, similar to this Zyberg's analysis of this ultraviolet non-trivial fixed points in 5 dimensions, etc., etc. So this way leads us maybe to some non-trivial effects in the ultraviolet also. So that's it. I have to finish. So that is just briefly what I tried to say. The dual partition function satisfies these non-autonomous equations of Penlever times. This follow from the autonomization of the Zyberg-Witten integrable systems. Natural picture in 5-dimensional theory. So these are Q difference equation. Yeah, so we even have more derivatives than academician Arbuzov. You have only finite number of. And that gives some further way of thinking about this interesting subject. Thank you very much.
Thank you very much. Let's thank the speaker for very nice presentation. Clear presentation of non-trivial mathematics also. So we have time for a few questions, maybe 2-3 questions.
In the case of M2 supersymmetric HL, in beta function, you have just first term.
Yes.
Without second one.
Yes.
These both are reparametrization invariants. So in
it's
the
just constant
model, you have second invariant coefficient is exactly 0, right?
Sorry, I'm lost. So in beta function, you just have one constant. This is 2n minus nm.
Generally, you have two first terms.
Yeah, but I'm not speaking generally. I'm speaking only about n equal to. Yes.
But the fact is that the second term is 0 in that supersymmetric case. If we take some theorem, calculate that two terms, and find that in some case the second coefficient is 0, if it indicates that we have some symmetry, some inverse question, if the second term
We
is
know the symmetry is n equal to.
So as I said about loop theory part, the people whose anniversary we're celebrating are much better experts than I. So, Dima, спасибо. Here, just one, nothing to add.
Are there any questions in Zoom, Alexander? No? More questions?
Argue whether you can say that beta function has non-perturbative contributions or whether it cannot have non-perturbative contribution. I would say that it's rather philological. What is funny is the story from 90s that this prepotential has lots of non-perturbative contributions. And there was, many attempts before Nekrasov to check it by direct instanton calculus. And as I remember, there were many people computing this, and they reproduced Seiberg-Witten result in both cases, when Seiberg and Witten were correct, and when they made a mistake. Effectively.
So let's thank the speaker again. Now we switch to the program which was initially supposed. I would say to next speakers that if you didn't understand, we had a shift of one talk from previous session. Now we start 4 Zoom talks, and the first talk is by David Broadhurst of multi-loop modularity. Please start.
It's a great honor to be able to speak at a 490th birthday party for the 7 samurai from Moscow. So I'm going to begin briefly by mentioning papers that they wrote when they were less than half of their current age and that influenced me deeply. And those papers go up to 5 loops. And my talk is what is the number theory content of counterterms, and also in the magnetic moment of the electron after, for counterterms after the multiple polylogarithms that we see up to 5 loops. What we will find is that in counterterms, multiple zeta values appear at 6 loops, polylogarithms of 6 roots of unity at 7 loops, and at 8 loops, modular forms obstruct reduction to multiple polylogarithms in the most beautiful way imaginable. When quantum field theory hits new numbers, she does it in an extremely beautiful way. And modular forms are of the essence for the magnetic moment of the electron at 4 loops, that continues at 6 loops. And again, we see beautiful modularity. And finally, as a grace note, I consider off-shell massive Feynman diagrams which determine through modularity the areas of the event horizons of black holes obtained by compactification of supergravity from 10 dimensions down to 4-dimensional black holes. Again, a wonderful connection, but all concrete Feynman diagrams. Okay, so what are the papers that I want to cite? Well, these guys were very young. We're looking here at 1974. Already they're looking at essentially the standard model, not just non-abelian gauge fields, but coupled to scalars and to spinors, and of course the self-action, the self-interaction of the scalars. And there you will find the 3-loop beta function of phi to the 4th theory, where of course 6 Riemann zeta 3 comes from the wheel with 3 spokes at 3 loops. Now we only have to go on to 1978 to see that Alexei has gone on to 4 loops, where 20 Riemann zeta 5 appears in the beta function of phi to the 4th. Here I'm noting work by Kostya and Nikolai, where they were looking at E plus, E minus, and also invoking some rules, which played a large role in my subsequent work. Here we also see a deep connection between the critical exponents of condensed matter physics and the anomalous dimensions of quantum field theory with Dima and Alexei. A wonderful paper here by Kostya with Andrei Katayev and Fyodor Tkachov using Gegenbauer polynomials in X space, which were enormously important to me when I went on to the 6 and 7 loop beta function of phi to the 4th theory. This great paper that's been the basis of full loop calculations in the standard model using integration by parts in d dimensions by Kostya and Fyodor. Work by Volodya, which was important for me. You don't have to use dimensional regularization to evaluate counter terms. Analytic renormalization can be sometimes more efficient. Here by Anatoly, we see a connection with work which I later did on massive Feynman diagrams, where I developed integration by parts for massive Feynman diagrams in response to the challenges of heavy quark physics. Here is the infrared R operation, which enables us to calculate L loop counter terms by only looking at L-1 loop 2-point functions. And here, the combination of all of this, the 5-loop beta function of phi to the 4th theory from Kostya, Sergei Gorishny, who died tragically young, Sergei Larin and Fyodor. It was a wonderful achievement. It wasn't right, but look how long it took to correct it, 12 years. I had the honor of examining Verena Schulte-Frohlinder's thesis, and the authors got together and we now know the definitive result. And by the way, I tell you that we now know the 6 and 7 loop beta functions of phi to the 4th theory. Kostya and Volodya reconsidered the R-star operation in a way that was slightly controversial and I won't comment on, but this was work that I studied. And finally, imposing my cutoff that the 7 samurai are still, each of them less than 35 years old, we have this method of uniqueness, which has been very useful to me, in which Dima actually proved that the 5-loop zigzag diagram evaluates to 441/8 Riemann zeta of 7. Okay, so what comes after 441/8 Riemann zeta of 7? Well, in 1985, I easily evaluated empirically the 6-loop zigzag diagram, this multiple of Riemann zeta 9, later proven using analytic regularization by Natalia Wazukina. And there were 3 other periods from primitive diagrams free of subdivergences at 6 loops. One of them was easy to evaluate. The other 2 were much more difficult, but a linear combination of them gave this weight 8 contribution of zeta 3 times zeta 5. Now, I had a very strong intuition that what we were seeing here at 6 loop was the first irreducible multiple zeta value, this double sum, m greater than m greater than 0, 1 upon m to the 5, n to the 3. But I didn't have enough digits at that time in the periods to make the analytic identification. Later, Dirk Kreimer and I did this and many other diagrams, and these periods, yes, do indeed, the third and the fourth period do indeed involve zeta phi 3 with this wonderful universal multiple of zeta of 8. As well as that, we found in 7 loop counter terms, zeta 3 phi 3, an irreducible triple sum of weight 11 and depth 3. And we gave a conjecture for the L loop zigzag diagram, which 20 years later was proven by Francis Brown and Oliver Schnetz. But we're still talking about multiple zeta values. We've got a long way to go. If at 7 loop counter terms, there were 3 numbers which Dirk and I evaluated numerically to 10 digits, but still couldn't identify. And, further work by me identified 2 of these. In the interim, deep mathematicians like Francis Brown have said, oh, David, you're going to encounter alternating sums. In fact, I ended up with a convincing fit in terms of only multiple zeta values.
May I ask a question, please?
Yes.
Do I understand correctly that you can calculate some 7 loop diagrams, but you
all
cannot calculate all of them?
All of them are calculated, as you will see. Next transparency.
You can make just complete calculation at 7 loop level?
Yes, it's complete. It's completed, including the minimal subtraction scheme. Please let me continue. So yes, there were 3 which we only had numerically. These are their values, and they have been proven by Eric Panzer and Oliver Schnetz, and they ended up with huge combinations of alternating sums, just as the mathematicians had predicted. But then when they used our multiple zeta data mine, which relates alternating sums to multiple zeta values, they ended up proving these expressions. Thank you for the question. Here is the final, most difficult diagram. At 7 loops. It's the most beautiful diagram down here. It's called P711 in the census of Schnetz. All other counter terms reduce to 6 roots of unity. Eric Panzer obtained it in terms of 4,589 weight 11 multiple nested sums of 6 roots of unity. I offered him a conjecture that this ought to be reducible to a 72-dimensional basis, and he had just about enough digits to end up with an analytic expression in that 72-dimensional basis with amazingly nasty coefficients. For instance, the coefficient of pi to the 11 in the square root of 7 times this period has in its denominator, there's 5 and 6-digit primes. There's led me to get really serious with 6 roots of unity, which I'd already encountered in massive diagrams, 3-loop massive diagrams. And I was able to build a data mine of polylogarithms of 6 roots of unity in which this condenses down to a single slide, which I won't show you, and no prime greater than 3 occurs in the denominator. But there's a very large amount of effort that's involved in doing this. Now I come on to where we go beyond multiple polylogarithms of roots of unity. At 8 loops, there are 41 primitive diagrams. Of course, one has to do renormalization of the diagrams with subdivergences, but those are not going to give new numbers. So the number content is in these 41 periods at 8 loops. And thanks to enormous amount of work, 33 of these are now known analytically. And moreover, 4 of the 8 undetermined cases are, by mathematical analysis, extremely likely to be reducible to multiple polylogarithms of unity. What I'm concerned with here is, first time in counter terms at 8 loops, what do we see beyond polylogarithms? And in the remaining 4 cases, there are obstructions to reductions to multiple polylogarithms of the most beautiful forms imaginable. When quantum field theory hits new mathematics, it does so like the textbook. So let's look at the 37th period down here. It's a 8-loop diagram. It has 16 edges. We have 16 Schwinger parameters, a projective integral, 15-dimensional projective integral. We can do in principle 12 of those 15 integrations. Of course, each time we will get multiple polar logarithms, but at the next thing, we only have to look at the denominator of the expression and ask, is it linearly reducible? Can I find one Schwinger parameter in which it's linear? In which case, we will go on to multiple polar logarithms. That stops after 12 integrations. And you have a three-dimensional integral of multiple polar logarithms of weight 10. But in the denominator, you have this beautiful function down here. Of course, you set one of the Schwinger parameters equal to unity for momentum conservation. You've got to integrate multiple polar logarithms of weight 10 with a denominator, which is a fundamental obstruction. This is a K3 surface. It's one of the most beautiful K3 surfaces you can imagine. And you can characterize it by a modular form. You do that very simply. You just count the zeros of this polynomial in finite fields in f of p, where p is a prime or a power of a prime. And then if I calculate the number of zeros when p runs from 1 to 10 modulo 11, and I calculate those numbers of zeros modulo 11, then I expect if there's a modular form underlying, then that will tell me modulo 11, the coefficient of q to the 11 in the Fourier expansion of that modular form. And it's the most beautiful modular form. It's the unique modular form of weight 3 and level 7. I just make it by taking the eta of z and eta of 7z, these classical objects, the eta of z, eta of 7z, I raise it to the power 3. That gives me weight 3 and level 7. And here in its Q expansions, these numbers are telling me, for instance, if I calculate the number of zeros mod 11, it's equal to 5 minus 6. And what about these? So these diagrams are not monsters. They're the most beautiful things you can imagine. It's just telling us that quantum field theory outgrows encounter terms at 8 loops, multiple polar logarithms. And you just find these beautiful eta quotients, the unique eta quotient of weight 4 and level 5, the unique eta quotient of weight 8, of level 8 and weight 3, the unique eta quotient of weight 6 and level 3. What could be more wonderful? So modularity is not something to be frightened of, it's something to embrace. Now we get on to the magnetic moment of the electron. You know, Dirac said it was one Bohr magneton. Schwinger told us that there's a correction of half alpha over pi. Peterman and Sommerfeld found zeta of 3, and also because there are alternating sums, log 2 at 3 at 2 loops. Laporte and Romidi found zeta of 5, but again, because they're alternating sums, they encountered a term here, which I identified as an alternating sum, which can be reduced to a single classical polar logarithm inside the unit circle. At 4 loops, we encounter much richer structure. So here I've taken this wonderful result of Laporte and split this very small coefficient of alpha over pi to the 4th into 4 terms. Here are the multiple polar logarithms of 1st, 2nd, 4th, 6 roots of unity. And here's a Bessel moment. This will be the hero of my story. And then there are more complicated integrals that are have integrands that are squares of elliptic integrals multiplied by logarithms. And then there are really subtle light by light terms. But this is the first place that we hit modularity in G-2. It's very easy to understand this one-dimensional integral. We have an electron of unit mass outside. The Fourier transform of that gives the regular Bessel function, and the 5, we have in the intermediate states, including 5 electrons. So we're going to see 5 powers of the Fourier transforms, the exponentially decreasing Bessel function. And it's only a polynomial in t and t cubed at higher powers of t are related by integration by parts. Now, this takes into things that are like elliptic integrals, but richer than elliptic integrals. And I go back to a bit of history. On the 30th of May in 1799, Carl Friedrich Gauss recorded in his notebook this discovery that this elliptic integral, which Euler tells us it's just an Euler beta function, so it tells us it's just gamma squared over 1/4 over gamma over 1/2, is the inverse of an arithmetic geometric mean. Now that's something that it converges enormously faster. Moreover, it's at a singular value in which this evaluates to a theta series. I mean, here you see not just exponential convergence, but super exponential convergence, the square of a theta series. This is the first singular value. In 1939, Watson, looking at multi-loop integrals and condensed matter physics, identified things that evaluate as the square of elliptic integrals and hence the fourth power of theta series, but at the sixth singular value. And there, by the Chandler-Selberg theorem, we find products of gamma functions, gamma of 1/24, 5/24, 7/24, 11/24. So now looking at three-loop sunrise, this will be external, one massive external particle and four massive internal particles. We don't see that in the magnetic moment of the electron because fermion numbers conserve, but looking at that sunrise integral, then I found that the sunrise integral itself with one Bessel function for the external particle and 4 for the internal particle. And here I've differentiated, and here I've cut a line and differentiated. All 4 of these Feynman integrals are evaluated in terms of a single number C that occurs also with its reciprocal. And this number C is related to a modular form. The determinant of that matrix is free of C. C is the square of elliptic integral, the fourth power of the theta function at the 15th singular value, evaluates the products of gammas of multiples of 1/15. But underlying this is a modular form made out of the same eta quotients as I showed you in the zero mass counter terms. It's a modular form of weight 3 and level 15. These are its Fourier coefficients. They define an L function. Instead of the zeta values where we take 1 upon n to the s, we include these Fourier coefficients in the numerator. This converges only for s greater than 2. But we can, through modularity, we can analytically continue it inside its critical strip and evaluate it at the 2 points, s equals 1 and s equals 2, which are related by modularity, end up with this exponentially convergent series involving these Fourier coefficients, and it gives us a sunrise integral on the 1 constant here. So now let's actually look at Laporta's problem, where he has 1 external mass and 5 internal masses, and integral t dt. This comes from differentiating that diagram. This comes from cutting an internal line and differentiating it. Again, there are these 4 numbers. Again, their determinant is a rational multiple of a power of pi, and underlying this is a modular form of weight 4 and level 6, again made as beautifully simple as you could out of this product of eta values. And and its periods, the Eichler integrals of this in the upper half of the convex plane, again, fantastically convergent because I can integrate from z is equal to a cube root of unity up to I infinity using a highly convergent Fourier expansions. The periods of this modular form give these 2 integrals. But these are the quasi-periods associated with a weakly holomorphic form, which took me quite a long time to discover that if you multiply this cusp form by this function of this weight 0 eta quotient, then you end up with a weakly holomorphic form that gives the quasi-periods in this part of the matrix. Here are the linear relationships between the 4 Feynman diagrams and the periods and quasi-periods. This matrix here is a beautiful matrix. It determines an intersection number, which is 1/12. And turning these back into hypergeometric integrals, that's not an efficient way of calculating them, but it's a way of making contact with canonical mathematics. We can relate everything to these 4 F4-3 series, z equals 1, with 4 arguments at the top and 3 arguments at the bottom, which are multiples of 1/6. And so this quadratic relation that applies to the magnetic moment of the electron can be translated into this hypergeometric series. At 6 loops, the story repeats itself. I won't go into the details. It's in my published papers. But again, there's a modular form. This is the modular form that determines when we have 7 massive particles in the intermediate state, and 8 Bessel functions. So what has this got to do with black holes? I've just about managed to rush you through all of this wonderful mathematical structure from counter terms and from the magnetic moment of the electron. Well, in 2019, Philip Candelas, Xenia de la Ossa, Mohammed Olney, and Duco van Straten announced a remarkable discovery on a 1-parameter family of Calabi-Yau manifolds with attractor points of rank 2. They were compactifying type 2A supersymmetric theory of from 10 dimensions onto a 6-dimensional Calabi-Yau manifold, Calabi-Yau 3-fold with complex structure. And they ended up with black hole, 4-dimensional black hole solutions whose areas were given by ratios of periods of modular forms of weight 4, and in their cases, level 14 or 34.
Sorry, may I remind you that you have 5 minutes more?
Thank you, and I'm bang on time. Thank you very much. As soon as I saw this, I said, oh, you're calculating Feynman diagrams. And they said, what? I said, yes, the family of Calabi-Yau manifolds that you're dealing with is very well known. It corresponds to the 4-loop sunrise diagram. And you just happen to be, instead of Stefano Laporta putting the external mass equal to the internal masses, you're putting the external mass equal to something different. And I was able to identify the external mass that they were effectively using, totally ignorant of Feynman diagrams, these string theories. And the level 14 weight 4 modular form, which I will show you, corresponds to a particular external mass and the level 34. What they're dealing with here are integrals where we have internal propagators, some of which we cut, and there's just an external mass Z here. And these integrals are related by integration by parts. There are a finite number of them, and what we want to know, what are the primitives? And what I was able to discover is that the differential equations for their Calabi-Yau periods were the same ones as the Feynman diagrams, but they were looking at the homogeneous solutions, where of course we want the inhomogeneous solutions for. So here's my final transparency. I think I'm on time. The external mass for the magnetic moment of the electron is 1. If I change the external mass, and that gives me this beautiful weight 4 modular form with level 6, whose periods and quasi-periods answer the Laporta problem. If I change the external mass to the square root of 17 minus 4, rather a small mass, then I obtain the periods and quasi-periods of a weight 4 modular form of level 34 that solves their black hole, one of their black hole problems. If I go to the spacelight point, I put the external mass equal to the square root of minus 7. Well, we know that just means when p squared equals minus 7 in the spacelight region, I obtain the level 14 periods. So what I was able to do is not only relate their results and identify numbers that they had not been able to identify analytically, but also produce the beautiful modular form. It's going to be just like in the counter terms for the phi to the 4th theory at 8 loops, just like G minus 2. And here is the weight for level 14 modular form. And moreover, I was able to identify the quasi-periods that go with it. But now we go inside the critical strip and we find the diagrams at the square root of minus 7 for level 14 that they wanted. There are 2 of them in the middle of the critical strip, and then at S equals 1 and S equals 3, they're related by modular transformation. But there's also a weight 2 modular form associated by an elliptic curve. We all know that elliptic curves are not really cubic, they're quadratic. And here's this beautiful modular parameterization of the elliptic form in the way that Andrew Wiles proved, among other things, Fermat's last theorem. And Kevin Akers and I were able to construct the weakly holomorphic forms that give the quasi-periods. And finally, I end just on time with the formula for the area of the black holes. The black hole associated with the level 34 modular form has an area 34 pi in natural units times things determined by the magnetic and electric charges, and this is one number V. And this one number V is a ratio of periods. So it's a ratio of Feynman integrals. And here's a Feynman integral. I take the sunrise diagram, I cut two of its internal lines, and I put the external mass equal to square root of minus 17/4. And then I divide it by the one in which I've cut just one internal line. And the same thing works at the square root of minus 7. So I end bang on time with a summary. Zeta values are enough to 5 loops, multiple zeta values at 6 loops, multiple polar logarithms of Roots unity at 7 loops, beautiful, wonderful modular obstructions at 8 loops. Sunrise diagrams involve modular forms at 3, 4, and 6 loops. I also know the automorphic forms at 7 loops. And off-shell massive 4-loop diagrams involve modular forms whose periods determine areas of black holes in compactified supergravity. And finally, my enormous thanks to my co-authors. I've listed them here, who grounded me in the great traditions of Russian physics and mathematics, and to all of those colleagues who encouraged me. But I think we should single out those people who are no longer with us. I remark that Vladimir Gert, who did so much to increase the expertise in computer algebra and quantum field theory, died in January of this year. And here's my hero, Dmitry Shirkov, who stayed with us till the age of 87, still encouraging us to work. And I remarked that one of the sadnesses of not being able to come to the Soviet Union as it then was because of restrictions meant that I wasn't able to meet Sergei Goloskokov, who died tragically young in 1988 and surely deserves to be mentioned among all of the people we're celebrating today. And I remind you that underpinning so much of this work abides the lasting legacy of Nikolai Nikolaevich, whose grave I visited when I first came to Moscow in 1992. So thank you for your attention, and thank you all my colleagues for this enormous contribution you made to my own work.
Thank you so much, and your work is closely connected to the works of the heroes of this conference we are celebrating here. So thank you so very much. We have time for some questions.
So David, thank you very much for your talk. I want to come back to calculation of these periods of massless integrals and ask, do we know anything about structure of functions in the final answer for not even dimensions, but odd dimension? Do we know some general rules about MZV, something like this?
You see what happens down there is you get the square root of the semantic polynomial. So you're dealing with a different type of motive. What the mathematician would say. I mean, I've evaluated counter terms in 3 dimensions, and there, for instance, I find Catalan's constant, which you at a very early stage, and Clausen values at strange points. Numerically, those calculations were done before the numerical calculations in 4 dimensions, you know, from which we use as empirical input to fitting things. They were done by Dutch physicists with enormous dedication, because they were really needed for critical experiments. Tolya Kotikov, if you're interested, Tolya Kotikov and I have a paper on all orders results for 3-dimensional critical exponents in the large N expansion, where we find not multiple zeta values, but multiple alternating sums. In some sense, odd dimensions have complicated critical exponents and interesting massive diagram, more tractable massive diagrams. In 4 dimensions, the critical exponents are easy, and the massive diagrams involve alternating sums.
Thank you.
More questions?
For any Feynman diagram, we have a clear algorithm how to write corresponding integral expression, right? Feynman or Schwinger parameterization. And their statement that expressions can be expressed as hypergeometric functions. is the class of even geometric functions rather wide to include all of that empirical relations? How you feel?
It's not really a meaningful question. I mean, I was asked this about the master two-loop diagram a long time ago, and someone said, "Oh, I've evaluated in terms of a Lorentz function." They've just done some very, you know, they've just done some simple Mellin-Barnes transformation, ended up with some multiple series, and said, "I've solved it," and found that once Lorentz had looked at it, you know, so that there's a huge literature on this. So you'll find a great deal of expertise of multiple series, but they all come from simple places. You know, so at the end of the day, we're interested in efficient calculations. I can get 10,000 digits for these diagrams in minutes. If you end up with some five-fold series that you say is a beautiful hypergeometric series, it's not going to be any good for you. You'd be better using Monte Carlo integration.
Thank you. We got a question from Zoom, please. Question from Zoom.
Excuse me, dear David, thank you very much for your talk. The question is, I've seen some interesting representation which is proportional to zeta 4. At present, I am looking on another screen on a very interesting to my mind and not very known paper, a theorem on zeta function of argument 4 by Andrei Peterman with different representations for zeta 4 functions, zeta 4 function. Do you know this paper, or if you know, can you comment on this paper something?
I don't think it's relevant to this talk, Andrei.
Huh?
It's a mathematical question you're asking. I don't think it's relevant to this talk.
Yes, that's a mathematical question. Different representations for zeta 4 function.
I know lots of representations for it.
So you are not aware of this?
The simplest of which is pi to the 4th over 90.
No, yes, of course. But probably I will send you the reference for this.
Thank you. Please,
we may discuss this privately.
Please send it to me and we'll discuss it privately.
Thank you.
Thank you, Andrei.
So thank you again, and we come to the next talk. And the next talk is by Burt Ovrut, and it's hidden sectors for heterotic series and Gaugino condensation. Is there a speaker? Okay.
Yes, hello. You hear me?
Yes,
we do. Everything is okay.
Okay, so I guess I will begin. Let me just get my watch in place here. I'd like to thank the organizers of the meeting for giving me a chance to speak. I really appreciate that. Let me larger screen. What I'd like to discuss today are heterotic M theories. These are strongly coupled heterotic string theories. But in particular, I want to discuss the hidden sector of these theories, and having done that, discuss Gaugino condensation that would occur pretty much automatically under these circumstances. The authors of this talk are the people below: Anthony Ashmore, Sebastian Dumitru, who is my student, and myself. So this stuff that I'm going to discuss actually works for any kind of realistic vacuum state of the heterotic M theory, but I'm going to look at a particular one, which is almost the MSSM, but actually has an extra U1 B minus L gauged symmetry. And so I'll call it the B minus L MSSM. And it was developed by all of the people that you see here. So it starts off with Hojava-Witten theory, which is a 10-dimensional theory, but it's an orbifold. So you end up with a 10-dimensional plane on one side, I should say 11-dimensional theory, 10-dimensional plane on one side, 10-dimensional plane on the other side. and a one-dimensional real line in between them, separating the two of them. One of them is called the observable sector, the other one is called the hidden sector, and then in between you have this in-between space. And what we're going to do is then compactify this down to a 5-dimensional theory with a 4-dimensional observable sector, a 4-dimensional hidden sector, and this 1-dimensional line in between them. How do we compactify them? Well, we're going to try to create a realistic theory here. That is essentially the MSSM. So when we compactify on Calabi-Yau threefold, and this is a particular threefold. It's a Schoen manifold. I don't have time in this talk to discuss any of the details of this, but this so-called Schoen threefold, and it has a fundamental group of Z3 cross Z3, which is important. Okay, so we have this freely acting Z3 cross Z3 isometry, which will be very important to us. The Hodge data is that H11 is H12 is equal to 3. So there are 3 Kähler and 3 complex structure moduli. In general, the complex structure moduli tend to naturally be very heavy at the order of the compactification scale. So we will ignore them in this talk, and I won't discuss complex structure at all. However, there are 3 real Kähler moduli. I'll call them A1, A2, and A3, and they will be very important in this talk, entire discussion. I'm just wondering if I'm better off like this, and you can see the pointer. So let me try this. So let's first start off on the observable sectors. That's one of the orbifold planes, and it starts off being 10-dimensional, but we're going to compactify it on a threefold, so it turned out to be 4-dimensional at low energy. But we're going to put a vector bundle on the Calabi-Yau, and this vector bundle will be chosen so that its structure group is SU4 inside of the E8 that lives on the observable sector. And again, we're choosing this in order to get a realistic specific theory, but you could do this in many, many different ways, but this is the one we're going to follow. And what we need is that this should be slope stable, which means that it has a gauge connection, which satisfies the Hermitian-Yang-Mills equations, which is a requirement of all of this. And we can show, it's very non-trivial actually, that inside of this 3-dimensional Kähler moduli space, that it is in fact going to be slope stable within a given region. So here's a projection of the 3-dimensional space. This is A1, A2, and A3 or something along those lines, and we projected them, and inside of this pink or red region, if you want, it turns out within that region of Kähler moduli space, this SU4 bundle will in fact be slope stable, and we have proof going along with all of that. Okay, so what happens here? Well, let's look at the observable sector. If we look at the observable sector, this E8, once there is a gauge bundle, spontaneously breaks to a spin 10 group or an SO10 group, if you wish. And this is a grand unified group. However, that's not what we're looking for. We're looking for the MSSM, but that's where this Z3 cross Z3 holonomy of X comes into play, because on one Z3, we can wrap a Wilson line, and on the other Z3, we can wrap a Wilson line. And these Wilson lines will spontaneously break the spin 10 symmetry down to SU3 color, SU2 left, and U1 hypercharge of the standard model gauge group. However, it automatically gives you an extra gauged U1 symmetry. It's a gauged B minus L U1 symmetry. And this thing we can show satisfies all phenomenological requirements. So you find out that the vector boson here gets a mass, and the mass is sufficiently heavy that it doesn't affect low energy physics, and so on and so on. But again, I don't have time to discuss all of that here. Okay, the beauty of all of this is that with the choice of the Schoen manifold, and the choice of this SU4 vector bundle, we get exactly the low energy spectrum of the MSSM. Exactly the spectrum. It's got 3 families of quarks and leptons. Each family has a right-handed neutrino chiral supermultiplet. And it has exactly 1 pair of Higgs and Higgs conjugate chiral superfields, which is the minimal amount that you would need in supersymmetry in order to have the Higgs effect and so on. So this is exactly right. And what we found remarkable about this, because it's hard to achieve, is that there are absolutely no other particles. There are no vector-like pairs of particles that you have to argue become heavy. They just don't exist at all. And there are no exotic fields of any kind. It's exactly the spectrum of the MSSM. So much for the observable sector, but again, there's going to be real physics living there. So we're talking about the real world here. There's the hidden sector, which is on the other side of this orbifold, of the Rojava-Witten orbifold. And we have to put a bundle there too as well. We could put no bundle there if we want, but that doesn't work. But you can put generically, you can have a bundle which is going to be a sum, a Whitney sum of a non-abelian bundle, call it script V, plus a sum of line bundles L. The non-abelian bundle can have some non-abelian structure group associated with it, but each line bundle will have a U1 associated with it. You can have an arbitrary number of them. In this talk, for simplicity, we are simply going to not have a non-abelian bundle, and we're going to consider only a single holomorphic line bundle. So the hidden sector here is just a single holomorphic line bundle. As we will see, when you embed it into E8, you have to take a direct sum with its inverse, but we'll get to that later on. But this is driven by a single holomorphic line bundle. And you then have to embed its structure group into the E8, and that's a non-trivial thing to do. And once again, I do not have time to go into that. That is a story of its own. But we have a single line bundle, and how do we describe it? Well, it's associated with the divisor of the Calabi X, and therefore it's given by this expression where L1, L2, and L3 are integers. But we want these integers, we want the bundle to arise from a Z3 cross Z3 invariant, equivariant line bundles, because we have this Z3 cross Z3 holonomy. So that puts an extra constraint on these integers. The L1 plus L2 mod 3 should be 0. So we can look at any line bundle that satisfies this particular condition. We do have to describe how we embed it, but this is the starting point. Okay. Now, we have to embed this into the U1. And this embedding, there's many ways to do it. You can look at the Dinkin diagram and see all the different ways you might embed a U1. It's important because once you choose the embedding, you then look at the commutant of that embedding, and that will be the low energy gauge group in the hidden sector. So it's important to give the embedding so that you know what the commutant subgroup is. There's also a bunch of constants in the theory. Here's one of them. Because you'll see little a all over the place. It doesn't matter, but I just want to point out that once you give the embedding, the generator of the U1 embedding, I'll call capital Q. This will be a 248 by 248 matrix representing the U1 generator in E8. You square it, you take its trace, divide by 4, and that'll give you some constant, and that constant appears all over the place. So we need to know the embedding to get the commutant subgroup, and we need to know the embedding so that we can compute the various numerical constants that come along with it. Okay. Now, we can also, in the space between the orbifold planes, between the observable sector and the hidden sector, there is a one-dimensional space, And you can have 5 branes that are located there. And these 5 branes wrap around holomorphic 2 cycles inside. And these 2 cycles get represented mathematically by a 2-2 form, which is the Poincare dual of this holomorphic curve. And we'll denote this by W. In this paper, we'll only consider a single 5 brane living in the bulk space in between, just for simplicity. You don't have to, but it's hard enough to analyze just one, let alone more than one, but you can. In general, the hidden sector will be at 0 and the hidden sector will be at 1 and the observable sector will be at 0, and the space will go from 0 to 1 in between, just our coordinate system. However, we will also use a parameter lambda, which will be this space minus a half. So in other words, this lambda goes from minus a half to a half. And this will just appear as a parameter in the theory. That'll be the location of the 5 brane in these coordinates, and we will choose it later on, and I'll discuss it later on. So having presented the constituents of this vacuum, that is the observable, hidden, and orbifold sectors of this particular vacuum, we get a bunch of important physical constraints on the theory, and we'd better solve them if we want this theory to be realistic. And I would like to emphasize that this theory turns out to be very realistic. So what are these constraints? Well, they break into 3 parts. First one I'll call the vacuum constraint, and there's 3 of those. One of them I've already shown you, the SU4 bundle on the observable sector should be slope stable, so that its connection satisfies the Hermitian-Yang-Mills equations. And I showed you that little pink or red area inside of Kähler moduli space. That's where it's satisfied. That region is given by these conditions, which I won't go into anymore. This is what specifies that pink region. So there's a reasonably large region of Kähler moduli space that satisfies the SU4 slope stability constraint. You also have an anomaly constraint that goes between, you have an anomalous piece, if you like, on the observable sector, on the hidden sector, and then you have an anomalous piece that's coming from, if you like, the 5 brane that lives in the bulk. And they had better sum up to 0 to have 0 anomaly, which allows you to express the W associated with the 5 brane in terms of other quantities. This L is the line bundle, the DIJK is the intersection numbers of the Chern-Calabi-Yau, but it doesn't matter. I'm not going to give any details from now on. This is the equation that must be solved. But to be anomaly free, WI, all of its components must be non-negative, and that's crucial. Then in the observable sector, there was this spin 10, which has some G1, some constant, gauge constant associated with it. And if I square that, it better be bigger than 0 because it's a real number, and it better be bigger than 0. Well, it turns out that that leads to this expression having to be bigger than 0. These are non-trivial things. They depend on lots of stuff, but that's one of the constraints. On the hidden sector, you have E7, or whatever you're going to embed this thing as, and it will have some G2 associated with it, and its square should be bigger than 0, and that's this expression over here. Okay. So where are we here? So we have to solve these vacuum constraints. So how are we going to do that? And we already showed that this SU4 constraint, how to solve it, that was given above. We found the solution, but the anomaly condition 2 and the condition 3 required line bundle and so on, we have to solve as well. But in order to do that, we have to specify a line bundle, and there are a lot of them that will satisfy this, but let me give you the simplest example. So here and henceforth, I will always choose the line bundle 2, 1, 3. And I will show you that that works for us. And if we choose this line bundle, then we have to discuss the other possible constraint conditions. But to begin with, if I choose such a line bundle, what is its embedding into E8? And there are many ways to embed it. And this is a long story of its own, but here's one way to do it. You will recall that there's an SU2 cross E7 maximal subgroup of E8. And if I decompose the 248 representation of E8, which is what lives on the in the hidden sector, that will decompose under SU2 cross E7 in the following way. Okay, and now how are we going to embed our line bundle into this? Well, we're going to say that the line bundle is such that when represented in the 2 of the SU2, it breaks up into 1 and -1. In other words, we're going to embed it in that particular way. The SU2 will break into U1, but with that particular embedding. And from that, you can figure out what the embedding inside of the 3 is, for example. So I'll just give you the answer. The 248 representation of E8 under not SU2 cross E7, but now the U1 cross E7, because we've embedded our line bundle in it, it decomposes in this way. And what happens is we get an adjoint representation for the E7, we get an adjoint representation here for the E7 group. We get representation that is a 56 under E7 and transforms in the unity under U1. Here's something that would transform, would not transform under the E7, but transforms as a doublet under SU2 and so on. So that's the expansion that we get. Okay, so it follows from the above expression. If I took that 248 and I wrote it out as a big 248 by 248 matrix, I'd squared it, take its trace, divide by 4, I'd find that this coefficient A is equal to 1. So all through those equations, you would set A equals to 1. The low energy gauge group is clearly given by E7 and cross U1, because that's what's left when you embed the U1. You notice that the U1 is the structure group of the gauge bundle, but it commutes with itself. So therefore, the U1 also enters the low energy gauge group. And when that happens, you tend to get an anomaly inside this U1. Viewed as a low energy theory, you would find that this thing has a triangle anomaly associated with it. And that leads this to be called an anomalous U1. And that's important, and we'll discuss some of that as we go on. But the bottom line is choosing the line bundle the way we did and embedding it the way we did, the low energy gauge group is E7 cross U1. So is there any solution in Kähler moduli space of the 3 constraints? And the answer is yes. So if we look at the 3-dimensional Kähler moduli space, so that's this thing, there's an A1, an A2, and an A3, we find that in this green region, constraint 1, constraint 2, and constraint 3 are all solved. So this thing works well, but we're not finished by any means. These are just the quote unquote vacuum constraints. However, there are some more constraints. We want this to be a strong coupled heterodic string, which requires the 5th dimension, that is this, the dimension inside the orbital, the distance between the observable and hidden sector, to be larger than the radius of the Calabi-Yau on which we've compactified, and that's given by this expression. V here is the volume of the Calabi-Yau. There's lots of terms that I'm just not going to bother to define here because I don't have the time to do it. But this is the expression that the space in between the observable and hidden sector is larger than the radius of the Calabi-Yau, and that leads you towards strong coupling. The larger you make it, the stronger the coupling. But anyway, we want this to be bigger than 1. And there's a physical constraint, and that comes down to the fact that in the observable sector, we had this SO10 spin 10 gauge group prior to breaking it with the Wilson lines. It had a coupling parameter, I'll call it GU. I called it G1 before, but the GU for the unification, the point of unification. We find that unification will occur at 3.15 to 10 to the 16 GeV, and that the value of this unification, the alpha value, GU squared over 4 pi, is 1 over 26.41. And there's a long story about how this comes about, but this is the standard that we get. And this is typical for usual grand unified SO10 theories. So this is what we're going to impose from now on. And when we impose that, we find that the original vacuum constraints, which was that green solution, the dimensional reduction constraint, which is that we get strong coupling, and these physical constraint that we get grand unification at the right scale, we find that there is a reasonably large region inside of Kähler moduli space, which is this brown region, which satisfies all of those things. Okay, so far so good, but we're not finished yet with all the constraints, because we talked about slope stability of the observable sector bundle, and it wouldn't automatically be n equal 1 supersymmetric because its slope vanishes, because it is an SU4 bundle. However, in the hidden sector, we're dealing with line bundles. So first of all, we better discuss its slope stability, and then its see whether or not it's supersymmetric in the hidden sector. So to do that, you have to go and actually talk about the embedding of the line bundle. We said there was a line bundle L. We've discussed various properties of it, but in actually to embed it properly into the E8, you have to embed it into that SU2 so that you get the 1 and the -1. And to do that, you actually have to write a rank 2 bundle, which is L plus its inverse. And this is the actual bundle we're dealing with. That's the one that embeds, as I showed you before, into the E8 so that it embeds into the SU2 as 1 and -1. But if you have such a bundle, then you have to discuss its so-called polystability, so that the slope of each of the factors should vanish, as well as the slope of the entire thing should vanish, which is immediate from this anyway. And that will be the case if this particular formula in terms of the 3 moduli is satisfied. And we can plot that. So if I look at moduli space, A1, A2, and A3, and I plot where this is true, we find this light blue surface sitting there, and any point on that surface will be slope stable, and it will also be n equal 1 supersymmetric. But I don't want to go into all the details of all of this. But you will find it's supersymmetric. The slope will have to vanish, and because the slope vanishes, slope stability and vanishing slope will make it n equal 1 supersymmetric. So we're talking about a completely n equal 1 supersymmetric theory in the observable and the hidden sector at this point. Okay, well, I showed you a region that satisfied all of the previous constraints, but here's the region in which we have n equal 1 supersymmetry and slope stability in the hidden sector bundle. So I should intersect them to find the region in which everything is true. And so I'll do that. And here's my little intersection picture. So I'm in 3-dimensional Kähler moduli space. This brown region was the one that satisfied the physical constraints that I talked earlier, all of the 3 constraints I talked about earlier. Here's the blue region in which the line bundle is slope stable and n equal 1 supersymmetric, and they overlap in this region, call it a magenta region. And if the vacuum is such that the A1, A2, and A3 of the Kähler moduli lie in the magenta region, then all of this physics is okay. All of the constraints are satisfied. You have n=1 supersymmetry, and so on and so on. It's a long story, but we're trying to be completely physical here and show that these string vacua actually have the correct physics. So you should lie in this magenta region, okay?
Excuse me, may I remind you that less than 5 minutes remains?
Okay, I'll try to.
Less than 5 minutes.
Okay, I run through it. One can calculate the low energy spectrum for this thing through the Euler characteristic. I'll just give you the answer. In the hidden sector, you'll find that you have an adjoint representation for E7. You have the adjoint representation for U1. You get 8 copies of a particle that is a 56 under E7 and doesn't transform under the U1. And you have 58 copies of things that are doublets under the U1, but don't transform under the E7. So one can calculate that in any situation. So given this thing, can we get Gaugino condensation? And since I don't have much time, I would just lead you through it step by step without much discussion. This is the theory we're looking at. It turns out that you will get Gaugino condensation, assuming that the coupling parameter becomes strong at some point, where in the hidden sector we're talking about here, is proportional to this unification scale cubed and has an exponential factor. And the thing here is that you'll have some function F2, which is given by the dilaton and the Kähler moduli. I'll define that in a minute. You have some constant here. And there's a coefficient V of L, which is from the renormalization group. It's the coefficient of the renormalization group. What is T? Well, if you take the real part of capital T, you end up getting A of I with a factor in front of it, and I won't discuss it anymore. The real part of S is given by the volume and then a factor that depends on the phi brane. And the various parameters we discuss enter the theory. The important thing is this B of L coefficient, which we have to decide. If we look at the hidden sector, then it has a E7 parameter. So we can look at the alpha associated with the E7 parameter, and it will run with momentum. So up at the high scale, this is what you have, but then it'll run down with momentum P according to the renormalization group, as long as B of L coefficient is bigger than 0. So we'll discuss that in a minute. But what we want to do is, if it's bigger than 0, this will run down so that the value at lower momentum of the coupling becomes extremely large. So its inverse will go to 0. So we will assume that we're going to pick a point P. It will hit a point lambda at which you get strong coupling, and we'll just approximate this as being 0 at that point. You don't have to, it just makes the math a little harder. So therefore, the value of this alpha 2, if this is 0, you can solve for the alpha coupling in the hidden sector, and it's given by this expression. The condensation scale can be re-expressed in this way. I don't have time to discuss it, but it depends on the unification scale in the observable sector and F1 and F2, which are these coefficients down below, these functions down below, and it will have, well, that's what it depends on. It has this B of L coefficient in it. W then can be rewritten. So W is set by the momentum at which the hidden sector coupling becomes strong coupling, and then it has this exponential factor with it. However, we're not interested in what supersymmetry breaking, this of course will be supersymmetry breaking. We're not interested in the supersymmetry breaking in the hidden sector, but we'd like to know what it is in the observable sector. But then they'll be gravitationally mediated over to the observable sector, so you end up dividing it by the M Planck squared. So the value of SUSY breaking due to this Gaugino condensation in the observable sector will go be proportional to lambda cubed over m Planck squared. So to finish this, if I take a specific example, I'll take this 213 example, then we know what alpha u is in the observable sector was chosen to be this. The function f1 and f2 are given by these functions in terms of the Kähler moduli. We are going to, for simplicity, choose lambda, which is the location of the 5 brane, to be near the hidden wall. We'll take it to be at 0.49. The volume would be given by this, and so on and so on. And the end result of this thing is the following. We know what the spectrum is for that particular line bundle. We calculated it, and we can calculate what the B of L coefficient is. It's 6, which is bigger than 0. And so what we'd like to know is what is the value of the supersymmetry breaking due to this Gaugino condensation in the observable sector of interest. That is this quantity. Well, we're interested in working in the magenta region because it's only the points in the magenta region which satisfy all of the physical constraints. So here's the magenta region, no longer magenta and blown up to look larger. And we're in moduli space at 1, A2, and A3 here. It turns out that if you're in this brown region here, then m SUSY in the observable sector will be between 10 squared and 10 to the 4th GeV. If you're in the darker brown region, it'll be 10 to the squared, 10 to the 6th, 10 to the 4th, 10 to the 6th GeV. And it goes all the way up to 10 to the 12th, ending up at around 10 to the 14th GeV. So you can get SUSY breaking from Gaugino condensation in the hidden sector of this physical theory that goes from low energy supersymmetry breaking all the way up to high energy supersymmetry breaking. And what you use here will depend on what kind of theory you talk about. For instance, if you do cosmological theories, at least the ones we've done, we tend to want larger supersymmetry breaking of this range. And if you're doing other kinds of theories, just low energy phenomenological theory, you tend to want to be around the TeV, somewhere in the middle here. Or somewhere around this 10 to the 4th GeV. So we can get that. So the bottom line is, that's the last slide here, is that there is a theory, there may be many theories of string theory which satisfy all these conditions. One that we discovered at Penn and I worked on was this so-called B-L MSSM. As far as we know, we've looked at the details of the physics of this thing. I haven't presented them in the observable sector, but let me just say that it gives the correct Higgs mass, it gives the correct W and Z masses, all of the supersymmetric particles are above their experimental bounds, et cetera, et cetera. We now know that we have a nice hidden sector, that you can spontaneously break supersymmetry in the hidden sector, bring it over to the observable sector. We can compute the soft terms. We have a paper on that if you care to look, but it'll be set by this scale, and we can get a low scale and high scale breaking and really make physics out of this, not just some mathematical model, but there's actually really physics embedded in. So that's what I wanted to express today. Let me leave it at that. Thank you very much.
Well, thank you. Let's thank the speaker, please. And let's have time for at best 2 short questions, not more.
First of all, thank you so much for a very interesting talk and for very impressive construction which you presented to us. However, as far as I understood, on our brain, we have usual MSSM, right? And we have already a lot of constraints from searches at Large Hadron Collider. Do you have any specific predictions for parameters of particles in low energy MSSM, except or in addition to those on the SUSY breaking parameter scale?
Yes, but we can.
Stop work masses or something. Stop 1, stop 2, I don't know.
Yes. So the answer is, which is the case with the standard model and still is the case here, the masses of the elementary particles are put in at 100 GeV and then run back up in the scale. So we put in soft terms, but these things are such that when we run them down, we will approach the experimentally observed value. We have no theory to predict them. However, and I want to make this as strong as I can because this is what we're working on now. Within this theory, or in general in string theory, one can compute the Yukawa couplings from first principles and get actual numbers from them. And you can also compute the what I call the Kähler metric in front of the kinetic energy for all of these particles. And then, of course, if you canonically normalize the kinetic energy, that would be a first principle prediction of the mass. And that can be done here. We haven't done it. We've been just simply putting in those values. But we have papers that show that the Yukawa couplings, for instance, are an integral over the Calabi-Yau of the various elements of the cohomology that's associated. So what I've used here is the cohomology. We can show that there are going to be three families of quarks and leptons, and that becomes from the H1 cohomology of the bundle that we use, the SU4 bundle. However, if you pick one of those, you can discuss the Yukawa coupling associated with it, and that will turn out to be related directly to an integral over the cube of the harmonic representative, the H1 harmonic representative associated with that particular particle. So yes, you can compute these things completely. We have not yet done it because it requires machine learning and maybe artificial intelligence to get this accomplished. And that's
Thank you very much. It would be very impressive to have.
So thank you again, and I'm sorry that we are running out of time completely. So let's thank the speaker and come to the next talk, please.
Okay, thank you very much.
So the next talk.
Hi, can you hear me?
Yes, our next talk is perturbatively renormalizable quantum gravity by Tim Morris. Please, 30 minutes, not more if possible.
Sure. So I'll just try to share my screen. I seem to have lost, no, I seem to have lost the ability to share my screen. I can't now see the...
We still do not see your talk on the screen. We hear you, we see you, but not your talk.
Yeah, I can see me, I can see that. I zoom, right. Some reason I can't see the buttons anymore to share my screen.
From our side, we try to fix things. From our side, we try.
So looks like you started sharing your screen, but just choose a window correctly, which you are going to share. Okay.
Yes, it's.
So we're definitely looking for something from your side. So it's not our.
Yes. Hang on. That, of course, is the thing I need to hit. Maybe that will help. I'm sorry, my computer has decided it needs to go through some trust procedure, which it hasn't done up until now. Right, pause share. Let's try. I'll try and stop the sharing and start again, see if that helps.
And what do you think? Maybe we interchange your talk. There is one talk more, and then you will deliver your talk after another talk. We have two more talks, your talk and another one. So maybe we interchange, and in the meantime, you try to fix the problem.
Yeah, I can do that.
Do you agree to that?
Yeah, sure. Can you leave me the chance to try and share, just so I can see if I can get it to work? But yeah, please go ahead. Yeah.
So we shall hear to your talk a little bit after another one, okay?
Sure.
So then we shall go to the talk by Sergei Kuzenko, non-compact duality, super-Weyl invariance, and effective actions. Is Sergei ready?
Yeah, just let me prepare.
Tomorrow's talk sharing screen.
Sorry. Yeah.
Oh, you are trying the last effort, yes.
I'm not now. Sorry. Go ahead.
Then Tim, let's first listen to another talk and then come back to your talk. Okay.
Sure.
So Sergey, if you hear us, please start.
Okay. Just a sec. All right. Okay. So it's pleasure. Can you hear me? Yeah,
yes, we hear you and we see the screen. Everything is okay.
Okay. It's great pleasure to participate in this remarkable conference. And I'm very grateful to the organizers for invitation. So I'm going to talk, well, my talk is based on a paper published last year with the same title. And so in Australia, when you submit grant application, you have to write summary in 50 words, something like that. And so I tried to summarize, well, main content of my talk in one sentence. So essentially, it's talk about implications of super-Weyl invariance and SL2R duality invariance on the structure of effective actions in supersymmetric theories with local couplings. Related early works. There are two related early works by Hugh Osborne and by Buchbinder, Plitnov, Zeitlin. Well, not directly related, but in principle, people did discuss similar ideas. So a brief outline of my talks. I will discuss several topics. I'll start with a review of U1 duality invariance in electrodynamics, also nonlinear electrodynamics. Then I turn to extension to non-compact duality, SL2R duality in the presence of dilaton axion. And then a main part, there will be main part of the talk, well, just local couplings in supersymmetric electrodynamics, and I end with some open problems. So electromagnetic duality is a very old concept. We know that Maxwell electrodynamics is simplest and oldest example of duality invariant theory in 4 dimensions. So this is famous Maxwell action, Maxwell Lagrangian. And if we consider the equations, consider the Bianchi identity and equation of motion, they have the same functional form. And therefore, one may consider so-called duality rotations. Well, you consider considers combination of F plus R F dual, just multiplied by a phase factor that induces the following transformation of E and B. And one can, well, see that Lagrange, well, Maxwell-Lagrangian changes, but the energy momentum tensor is invariant under one duality transformation. So, so that was Maxwell electrodynamics, free theory. And so in 1938, Schrödinger demonstrated that so-called Born-Infield theory also possessed one duality invariance. And further developments appeared in supergravity time. Well, in the 70s, many famous people noticed patterns of duality in extending supergravity. And then there was developed general theory of duality invariance in 4 dimensions by Gaillard, Zumina, Gibbons, and Rashid. Then that theory was extended to higher dimensions, again, Gibbons, Rashid, Araki, Tani, Aschieri, Brace, Mararia, and Zumina. So it's around, well, in the year 2000, Stefan Tyson and I wrote 2 papers and in which we developed general theory of duality invariance for n=1 and n=2 supersymmetric nonlinear electrodynamics. Well, main motivation was the fact that partial supersymmetry breaking often implies duality invariance. And so, well, so a year later, there was remarkable development by Ivanov and Zubnik. They proposed formalism to generate one duality invariant theories by putting forward a formulation with, well, in which duality invariance was equivalent to manifest one invariance of self-interaction. So now just in general case of electrodynamics, so what I showed you for Maxwell theory. So say if we consider nonlinear model, say just Born-Infield theory, then equation of motion becomes nonlinear, but we can write Bianchi identity and the equation of motion in well, the same functional form, and one can consider duality transformation, transforming F into G and vice versa. So with G prime determined by some new Lagrangian always exists. It can be shown, and non-trivial, well, the game becomes non-trivial if we require new Lagrangian to be the same. So, well, theory, well, in this sense, theory becomes self-dual. And then, so requirement, it can be shown that requirement of self-duality implies that only one duality transformation can be consistently defined in nonlinear case. And Lagrangian must be a solution of so-called self-duality equation proposed by Gibbons, Rashid, and Gaillard-Zumina equation, Gaillard-Zumina. So, so that self-duality equation can be, well, one duality invariant theories possess remarkable properties. Well, in general, every one duality invariant theory, well, is characterized by the energy momentum tensor that is duality invariant. So in the presence of dilaton and axion, duality can be extended to non-compact SL2R. I will discuss that soon. And every one duality theory is self-dual under Legendre transformation. So, well, Legendre transformation for electrodynamics is just defined in 3 steps. We introduced first order Lagrangian with F being unconstrained, and we introduce dual field that enforces Bianchi identity. So since F is unconstrained, we can integrate it out using its equation of motion, and then well, Lagrangian becomes function of dual field strengths. And if the original Lagrangian obeys self-duality equation, then LD coincide with L. Theory is L-dual. So, self-duality equation can be rewritten in terms of, well, just simple differential equation. It can be recast in a simple differential equation if we write Lagrangian as a function of electromagnetic invariance. So there are two invariants. We can combine them in a complex combination, and then self-duality equation is equivalent to the following equation on the interaction. And the simplest solutions of this equation: Maxwell theory, Born-Infield theory, and last year they appeared. Surprise! People, well, 4 people, Bandas, Lechner, Sorokin, and Townsend, discovered conformal Ivan duality invariant electrodynamics. It's one parameter extension of Maxwell electrodynamics. It's brand new theory, well, not much studied. So, so far I talked about Ivan duality invariance, and in the presence of dilaton and axion, duality, well, compact duality group gets enhanced to non-compact SL2R. And this is achieved by deforming Lagrangian this way. So tau here is a complex field combining the axion and dilaton. And duality transformation now acts both, duality transformation acts on field strengths, the equation of motion, and also on local couplings. So local couplings, dilaton, axion, they parameterize homogeneous space SL2R over U1. And now, so this deformation works for arbitrary U1 duality invariant theory. So just we consider, well, just arbitrary solution of self-duality equation, and we modify, well, we introduce dependence on dilaton and axion that way. And this is, well, so resulting theory possesses SL2R duality invariance. So, well, the simplest model in that family, Maxwell electrodynamics, leads to, well, just to this matter couple Lagrangian. And what is special about this model? It is SL2R duality invariant, and it is conformal. So, well, while invariant in curved space, conformal in flat space, and tau bar here are local couplings. Now, so this theory, well, it looks very simple, but if you quantize it, it's kind of non-trivial because, I mean, if you go through Fadeev-Popov procedure and then try to evaluate effective action in curved space, you'll see that a kinetic operator is non-minimal, so standard heat kernel techniques do not apply. You have to work hard in order to evaluate the effective action. So let me consider the effective action. So I call it just gamma, which is functional of tau and tau bar. So it is obtained upon integrating out electromagnetic field. So both, in the quantum theory, both Weyl and rigid SL2R duality transformations are anomalous. However, the logarithmically divergent part of the effective action must be invariant under this transformation. And the general part of logarithmic divergence was found by Hugh Osborne. Actually, he computed the logarithmically dependent, logarithmically divergent part of the effective action. And so this is high derivative sigma model. So we should think of tau and tau bar as fields parameterizing a closed space, homogeneous, Hermitian symmetric space SL2R over U1. And so, nabla here just a Lorentz covariant derivative, and so curly D is target space covariant derivative. So this Lagrangian is manifestly a SL2R invariant. So if you just, that's basically, well, that's the reason why we introduced D2 tau. And in addition, so the action generated by L is Weyl invariant. So the Weyl invariance follows the Weyl invariance of that action follows from the fact that the following fourth order operator introduced for the first time by Fradkin and Zeitlin in 1982 is conformal. So the same operator was rediscovered by two other people in by Panetz in 1983 and Reigert in 1984. And so essentially, this is just Osborne's work, 2003, and soon after Osborne's works, several people tried to extend his construction to supersymmetric case. And so success, no success was achieved until last year. And perhaps the main reason for that are the following. N equals 1 supersymmetric extension of the Fradkin-Zeitlin operator was constructed only in 2013. And a second reason, technical, if we compute the effective action corresponding to the vector multiplet coupled to the dilaton axion multiplet, and this is the model for the vector multiplet coupled to the dilaton axion multiplet, then the effective action involves functional determinants of non-minimal differential operators, and those are much harder to evaluate than in non-supersymmetric case. So you need, just superfield, generalized superfield heat kernel techniques, and they're not well developed. So now I would like to, to show you supersymmetric extension of Fradkin-Zeitlin operator, and for that I need some facts about supergravity. So, just first of all, I'll show you famous Green-West-Zumino superspace geometry. It's a supergravity analog of Lorentz covariant derivatives in general relativity. So this is just superspace general Lorentz covariant derivatives. Well, formally they have the same structure, and in general relativity there is field bind, there is Lorentz connection, and derivatives obey certain constraints such that there remain only 3 independent objects. So chiral scalar R, which is generalization of scalar curvature, W alpha beta gamma chiral, which is generalization of self-dual Weyl tensor, and G, which contains at the component level traceless Ricci. So now supersymmetric, analogs of Weyl transformations were introduced by Howe and Tucker long ago, and here they are. Super-Weyl transformations are generated by a chiral parameter. Well, it's chiral, but otherwise unconstrained, and you can see that W transforms homogeneously. It means it just it's really analog of the Weyl tensor. And now again, I'm ready to show you a supersymmetric extension of Fradkin-Zeitlin operator. And here, I should start with a story. Around 2006, I was visiting Germany, and several people asked me for a second order, for conformal second order operator acting on chiral scalars, and I said that it doesn't exist. So conformal second order, it's a fourth order in spinor derivatives, and and so essentially, I convince people that such an operator is impossible to construct, and my statement in principle is still correct, but so the equation was not correctly formulated. So the right operator is 6th order in spinor derivatives. At the component level, it gives right 2nd order differential operator. But so this operator that we constructed 8 years ago, so it is conformal. The fact that it's conformal in this equation. So when we just, if you consider two super-Weyl neutral chiral scalars phi and psi, then this property of the operator shows that this integral is super-Weyl invariant. And now you can leave chiral integral to full superspace integral. And here you see that we end up with 4th order operator. But this operator is not conformal because of that sector. That sector tell us that its operator transforms inhomogeneously, but that part disappears upon evaluating chiral project. So now, we just got this. Once we have supersymmetric extension of Radkin-Zeitlin operated, it become possible to extend Osborn's result to supersymmetric case. So now, I'll show you some general statement, just general results. So if we have U1 duality invariant supersymmetric electric dynamics, linear, non-linear. So then it can be coupled to dilaton axiom such that the resulting model is SL2R duality invariant. So the original U1 duality supersymmetric electrodynamics is it corresponds to the case when phi is frozen, a just imaginary unit. So in the presence of arbitrary chiral scalar phi. So this is the model we obtain. And so superconformal model corresponds to the case when we just start with free vector multiplier. So superconformal model corresponds to vanishing self-coupling lambda. Now, so just I restrict my attention to that particular case. And I'm interested in evaluating effective action. So I integrate out vector multiplet by following Fadeev-Popov procedures. So there should be Gauss fixing, there should be Fadeev-Popov operator, etc. Determinant, not operator, determinant. And so I'll skip those steps, but what follows from general principles is that logarithmically divergent part of the effective action should be invariant under SL2R rigid transformation and also under super-Weyl transformation. So we can ask question more general. Well, essentially it should be a super-conformal high derivative, super-Weyl invariant, and SL2R invariant sigma model. But we can ask more general question. Suppose I have a Kähler manifold with Kähler potential K. And question is, can I construct a high derivative sigma model that is super-Weyl invariant or super-conformal in curve space? So with dynamical fields taking values in that Kähler manifold, and the answer is yes. So, and the most general action is the following. So, okay, phi I is just chiral superfield taking values, parameterizing Kähler manifold. So Gi, so this is Kähler metric. G alpha alpha dot is field strength, just one of the curvatures. R is Riemann tensor of the Kähler manifold, and this is target space covariant derivative, if you like. So there are three possible structures in the action. So this is high derivative structure, then one structure involving Riemann tensor, and finally one term with one term involving.
We lost your talk. We lost your talk on the screen. We see you, we hear you, but we lost your talk.
We lost sharing.
Sorry. What about now?
No, it's okay now. But let me remind you that you have 5 minutes.
Oh, I'm almost done.
Only 5 minutes, sorry.
Almost done. So, well, essentially, well, this is just the most general super-Weyl invariant, and it possesses all isometries of the Kähler manifold. Well, strictly speaking, I'm interested in SL2R over U1. So if my manifold M is that manifold, then so I just, well, I should specify this action to that particular manifold, but it's more general result. Now, I can, well, next question, what is most general structure of super-Weyl anomaly? So essentially the same contribution that appeared in the action, the same contribution that appear in the action, they can be seen in the general structure of super-Weyl anomaly depending on the local couplings. So super-Weyl anomaly also contains purely supergravity dependent part. Here it is, and it was computed long ago. Now, so the rest is just calculation of the effective action. This is hard work, so it's, well, it just occupies most, well, just half of the paper. But, well, as I said, it's just calculation, so I skip all details concerning generalized heat kernel technique and etc. anomaly calculations. And so I give final result for the model under consideration. It's vector multiplet coupled to dilaton and axion superfield. So divergent part. So now, well, so the above general results are specified to the case of SL2R factorized over, well, to the, well, over U1. So this is divergent part of the effective action, and here I have super-Weyl anomaly. So super-Weyl anomaly is manifestly SL2R invariant. So now, just I'd like to mention two interesting two open problems. What I considered so far, it was n=1 story. So nothing is known about n=2 story. So in the n=2 case, we have to consider, we have to take a vector multiplet, abelian vector multiplet, and couple it to background chiral superfield. So in the presence of supergravity. Well, a blackboard V here, it's a prepotential. Prepotential, we have to do calculation in terms of unconstrained prepotential. There are several options for prepotential. Perhaps the most interesting option is harmonic prepotential introduced in Dubno by Ivanov, Galpeina, Givetsky, Sakachi. So there are different options, but so it would be interesting to compute just logarithmic divergent part of the effective action corresponding to this model. it would be interesting to compute super-Weyl anomaly. So no results so far. But well, there is what we know what we should expect. It's there was work by several people: Gomez, Kuzenko, Margotsky, Schwimmer, Zaver, Tyson. And essentially, well, they were interested in local couplings in n equals to theories, and local couplings here in X. And so, well, logarithmic divergence in such a theory should be, well, just should be of this type. It's integral over full superspace of Kelly potential. So it's high derivative theory. So, well, X is super-Weyl invariant, and then, well, properties of n equals to superspace integral tell us that the action is Kelly invariant. The action is super-Weyl invariant in curved superspace. But now we can take this model and reduce it to n equals 1 superspace. Every n equals 2 chiral superfield is a combination of 3 n equals 1 superfields, chiral. So phi, omega, and z. And now, if you just integrate out 4 Grassmann dimensions, you end up with the following model. And most interesting part is what appears in the first line. It is exactly a sigma model considered earlier, well, high derivative sigma model. So what is interesting is just a relative coefficient between so kinetic term and curvature dependent term. Yeah. It's absolutely fixed. There is no term involving product of two metrics. And so second open problem concerns, well, just again, n equals 1 story, but with several vector multiplets. So there are some general results. So if we have n vector fields, abelian vector fields, then maximal duality group is UN. So that compact duality group can be enhanced to SP2n, R. So in the presence of scalars parameterizing the following Hermitian symmetric space. So now we can consider just simple model, n vector multiplets coupled to matrix chiral superfield. So it's n by n matrix symmetric and with positive definite imaginary part. So such such superfields parameterize this Hermitian symmetric space. And then the problem is to compute the effective action corresponding to that model. This has never been done. And so in my opinion, it's very interesting technical problem. And well, I expect that logarithmically divergent part, it will be exactly sigma model of the type I described, but it's a problem for the future. Thank you very much.
So let's keep the speaker. Sorry, we have time only for one short question, maybe two very short questions. Okay, very short question, please.
You considered dual extension of linear models, and why we are interested in nonlinear extension? Because in linear case, we have not localized finite energy particle-like solutions, right? If any of the considered models, starting from dual symmetric electrodynamics, you have some localized solutions like finite energy, monopole, solitone, and so on. Because in that case, we will have the observable predictions. For example, the dark matter candidates and low energy, and so on. Experimental test.
So what question?
Sergey, did you get the question?
Any particle-like solutions for that?
Sergey, did you get the question?
No, I don't understand. Motivation was different. I didn't look at solutions. You see, it was about a local couplings in field theory. So it's like, so once we know dependence of the effective action on local couplings, we can compute, we can generate correlation functions. So it's like gravity. So I was not interested in solutions.
And thank you again.
Tim, can you hear me?
I can hear you. Can you see my screen?
Try to make in 25 minutes to leave 5 minutes for questions to your talk.
Sure. You can see my screen?
Yes, now we can see it. All right.
Excellent. Yeah, I had to reboot my iPad, but now it's behaving.
I think you can start.
Okay, thank you. Okay, well, thank you for the invitation to give this talk. Happy birthday to all 7 of you, and a special shout out to Dimi. I want to talk about perturbatively renormalizable quantum gravity. So that is work that I've been doing over the last few years and is published in these papers here. What do I mean by perturbatively renormalizable quantum gravity? I don't mean the usual way of thinking about quantum gravity as a effective quantum field theory. I mean more that it could be set up as a genuine quantum field theory like QCD or Yang-Mills, strictly speaking, and a perturbative quantum field theory as well. So it's based about, if we talk about it in Wilsonian terms, you have to think about an ultraviolet fixed point, and if it's a perturbatively continuum limit, that is just the Gaussian fixed point, that which is just free field theory. And then you have operators in space-time dimension 4, you have operators greater than dimension 4, which are irrelevant, and their associated couplings don't survive the continuum limit, they flow into the fixed point. And the continuum limit is parameterized just by the relevant and marginally relevant couplings that form this so-called renormalized trajectory. So the aim is to see whether we can actually, after all, set up such a thing for perturbative quantum gravity. So as everyone knows, quantum gravity does not have a perturbative continuum limit. The way you see that in the Wilsonian terms is as follows. So first of all, to use the Wilsonian renormalization group, I need to use Euclidean signature. And then the Einstein-Hilbert action looks as follows. Its natural coupling constant is kappa, 1 over the Planck mass, or equivalently the square root of Newton's constant. And to form the perturbative continuum limit, we want to expand around flat space. And if you do that, this action looks as follows. Here is the Gaussian fixed point, the free field theory of just free gravitons. And then you have an infinite series of interactions. And the problem is that even the simplest interaction here, the 3 graviton vertex, is a dimension 5 operator, so it's irrelevant. And so when you take the continuum limit, all these interactions fall away and you're just left with free field theory. But formulated in this way, this theory has another problem, formulated in Euclidean signature, which is that the action is unbounded from below. It has to be because it's proportional to the scalar curvature. And scalar curvature can be arbitrarily positive or arbitrarily negative. And if you follow the signs correctly, it's actually the positively curved manifolds that are the problem. So these guys many years ago noticed that this was a problem. In particular, it means that the partition function does not even naively converge. And they showed that the problem lies in the so-called conformal factor that you can think of as, roughly speaking, the overall size of the metric. And you can see it even at the free level. If you take the fluctuation field and you divide it into a traceless part, which we can think of as roughly speaking the graviton, and the traceful part, which is again this conformal factor. And then if you choose a gauge that decouples the two, you see the problem in the wrong sign action for the conformal factor. And I want to argue that that might be key to solving the first problem of renormalizability. So the idea is as follows. I mean, the partition function really doesn't make any sense anymore, not even naively. But you can phrase quantum field theory instead of in terms of an integral formulation as a differential formulation through the Wilsonian renormalization group. So in the continuum, that is what Wilson called the exact renormalization group and what is more often these days called the functional renormalization group. So it's a functional differential equation, and it makes sense even with this wrong sign. But as we will see, the wrong sign does have profound effects upon it. So the idea is to junk this and define the continuum limit, the quantum field theory, directly through the Wilsonian renormalization group, which is anyway a more meaningful way of trying to understand what the continuum limit is. So to describe what profound effects the wrong sign has, I first need to remind you what Wilsonian renormalization group looks like with a right sign kinetic term. So just take a single component's real scalar field with the right sign kinetic term. And for the purposes of this discussion, we can just take linearized interactions, non-derivative interactions, so an effective potential. If you do that, all versions of the Wilsonian renormalization group just collapse to this equation. And what this equation is telling you is how the effective potential that goes into the Wilsonian effective action changes as you integrate out more modes. So lambda here is some effective UV cutoff. And as you lower the cutoff, you integrate out more and more momentum modes. And at this linearized level, the only thing you're left with are quantum corrections, which are tadpole integrals. So on the right-hand side, you have the effect of computing tadpole integrals on this effective potential. This is the tadpole integral here. It's regularized in the UV by this effective cutoff lambda, so it goes like lambda squared. It's a one-loop integral, so it goes like h bar. And its exact answer is non-universal. It depends upon how you regulate, and that's captured in this number A here. So to complete the Wilsonian renormalization group, you need to work with dimensionless variables made dimensionless by this effective cutoff. And that's this flow equation. And if we separate variables, we get an eigenvalue equation. And this eigenvalue just gives you, is called the renormalization group eigenvalue. And it just gives you the dimension of the conjugate coupling. So this operator here is an operator of definite scaling dimension, what I like to call an eigenoperator. So this is scaling with some definite dimension, and the coupling, mu is just the standard arbitrary energy scale. The coupling also has definite dimension given by lambda. Now the nice solutions to this equation is of Sturm-Liouville type, and the nice solutions are a discrete set, which are just polynomials, in fact, Hermite polynomials in this field phi. So they have some highest power, and these lower powers are just generated by these tadpole corrections. And the scaling dimension of this operator is given by the power of the highest term. So if I were to continue this, and you can continue it to nonlinear orders and do perturbation theory in the couplings, you would just reproduce the standard Feynman diagrams way of doing perturbative quantum field theory. In particular, for n 5 or greater, these are all irrelevant operators and fall away in the continuum limit. Phi to the fourth is marginal, and the only relevant operator is actually the mass. Okay, one other thing that I should mention is that this flow equation is, in fact, just the heat diffusion equation in disguise. Small change of variables gives you the heat diffusion equation. Mathematically, it's parabolic, which means that its Cauchy initial value problem is only defined in one direction. And what that means is that if you start with some arbitrary bare potential up here, and use the flow equation, you're guaranteed a solution towards the infrared, which is the natural direction you would have expected to exist. But if you start with some random bare potential and try and flow in the other direction, you're almost certain to fail. It doesn't mean you can't flow all the way to infinity, but you have to choose the potential very carefully. Roughly speaking, that's the same problem as renormalizability, the fact that this will be controlled just by a small number of couplings. Now, I said that the solutions to the eigenoperator equation were the nice ones in the Sturm-Liouville sense. What did I mean by that? I mean that if you pick this set of polynomials, they span a space, span a Hilbert space, in fact, and that space is the space of perturbations which are square integrable under the Sturm-Liouville measure. Now, this is an underemphasized point in the Wilsonian renormalization group, but it is crucial. It's how you get universality and all the lovely effects of quantum field theory, ultimately, because it tells you that you can take an arbitrary perturbation and expand it uniquely in a convergent series, convergent in the square integrable sense, in terms of these operators with definite scaling dimensions. And after that, you see that infinitely many of these are actually irrelevant and their couplings fall away. You're left with just the relevant couplings, and that's how you get this universal description of so many phenomena out of quantum field theory. So these operators actually happen to be, in fact, orthonormal under the Sturm-Liouville measure. Okay, so what happens now if we change the sign? Well, at first sight, not very much. The flow equation is the same as before. It's just that it has a plus sign on the right-hand side now. The eigenoperator equation is the same as before, but with a plus sign. But now the nice operators of this, in the Sturm-Liouville sense, the ones that actually span a space where you're guaranteed convergence, are completely different. So these operators span a space of perturbations that are square integrable under the Sturm-Liouville measure, but that Sturm-Liouville measure is now exponentially growing. So it tells you you have to use this bunch of operators instead. These are solutions to the eigenoperator equation, but they're also square integrable, in fact, orthonormal under this measure. And they are exponentially decaying with respect to the conformal factor field. And they're actually all negative dimensions. So this is dimension one, minus one rather, and you have a tower of operators built on top of this just by differentiation, which are ever more negative dimension. The other interesting feature of this is that by changing the sign here, it's still parabolic in nature, this equation, but now the guaranteed direction in which the solution exists is towards the UV. So these operators are non-perturbative in Planck's constant, in h bar. The decay constant set by 1 over this tadpole integral, which is a one loop integral. And so all of these guys go like e to the minus 1 over h bar. So that's typical of a non-perturbative effect in quantum field theory. Renormalons and instantons do the same thing. So that's going to mean that we are going to have to work non-perturbatively in h bar, but we can still work perturbatively in the couplings. And as I said, you have to be careful to choose a solution going in the reverse direction to the natural one for the differential equation. But you can do so. You can choose a bare potential that does exist all the way to the infrared, where you've integrated out all the modes. And if you do that, what you find is a new effect takes over, which is at some intermediate scale, this potential will stop being square integrable under this Sturm-Liouville measure. It'll exit this Hilbert space. And at that point, its behavior at large field freezes out. So dependent on the choice of couplings, you get some characteristic amplitude suppression scale, which survives all the way down to when you've integrated out all the modes and formed the physical potential. And you'll find the physical potential decays with this characteristic amplitude suppression scale. Okay, now let's put all the fields together for quantum gravity. We also have the gravitons and the ghosts, and they have the right sign kinetic term. So their natural interactions are polynomials. But the conformal factor has to be introduce interactions through these delta operators, these exponentially decaying operators. And the structure of the quantum field theory is then as follows. You have polynomials with these guys and all the other fields and space-time derivative of those fields. So you have some highest order monomial plus tadpole corrections. Now, no matter how high a dimension monomial this is, you can always find one of these delta operators, because they're negative, increasingly negative dimension, that the combined operator is actually relevant. And in fact, all the higher n delta operators will also give you relevant operators. So summing over all these relevant operators, you get a coefficient function, which is parameterized by all of these relevant couplings, and they appear beyond a certain minimum level. So that's the structure that we get. We get this coefficient function times monomials in everything else. Now we need diffeomorphism invariance, or rather the quantum version of diffeomorphism invariance, which is given by the BRST invariance of the theory. And you can prove that actually these coefficient functions provide an obstruction to implementing this diffeomorphism invariance. It's kind of clear from here already that this will never be zero on the right-hand side, while this thing is a non-trivial function of the field. And these things are non-trivial functions of the field because they have to decay with this characteristic amplitude suppression scale at large field. However, quite naturally, if you consider the limit in which all scales are much less than this amplitude suppression scale, or what's the same, keep the other scales fixed and send this to infinity, then that same statement that this field goes with this characteristic scale, decays with this characteristic scale at large field, means that this function now tends to things that are basically constant. So in that limit, you find you can recover BRST invariance. So let me give you a simple example. So this is the 3-graviton vertex. Again, the first of the tower of irrelevant monomials you get out of the Einstein-Hilbert action. And it's dimension 5 already. But if you choose the underlying couplings in this way, as powers of the amplitude suppression scale, and with some mass dimension -1 proportionality factor, then these guys are all relevant. Actually, G0 is marginal, but the rest are relevant. And they sum up to a coefficient function that does indeed satisfy the linearized flow equation, and whose physical limit is just kappa times this exponential decay. And when you send this amplitude suppression scale to infinity, you just get a constant kappa. And at that point, you recognize that this is the kappa that you want in the Einstein-Hilbert action. It's basically Newton's constant. But you see that Newton's constant isn't there as a fundamental coupling. These are the fundamental couplings. This constant arises as a kind of collective effect of all of these couplings in much the same way as the amplitude suppression scale does. Okay, well, we've taken this to second order in kappa. So it has to be non-perturbative in H bar. So you find you have to sum over the so-called melonic Feynman diagrams, and then check that you have a sensible flow, singularity-free flow from infinity right down to 0, so that you can form this continuum limit. And you can show you can do that. And actually, when you take the limit in which the amplitude suppression scale goes to infinity, what you extract are the standard perturbative quantum gravity diagrams you would get at one loop. This construction seems to work to higher orders. So what we have here is a construction that's crucially different from other quantum field theories and indeed other conceptions for quantum gravity. But what just falls out from the requirement that we use the right operators in this flow equation and from this crucial minus sign is that we get a picture like the one I showed you at the beginning. You've got a UV fixed point, which is nothing but the Gaussian fixed point, the free field theory. You have a renormalized trajectory and relevant couplings that are coming out, but you have infinite number of these relevant underlying couplings. And you have this natural crossover scale at which this renormalized trajectory smoothly enters the diffeomorphism invariant theory space. And then when you take the various limits, you get diffeomorphism invariant amplitudes out. The problem is that at higher orders, there doesn't seem to be any reason why you shouldn't end up with effective diffeomorphism invariant couplings for the higher powers of curvature and so on, and thus reproduce in a different way the problems you have with perturbative gravity. But there is a hint that it's not quite so depressing, because so far I've been treating the graviton sector and the conformal factor sector as though they were could be treated separately. And in particular, I've been treating the graviton sector perturbatively, order by order in kappa, where you can just use polynomials of the graviton. But in truth, that's not true. That's not the way it works. The Einstein-Hilbert action is non-polynomial in the graviton. There is no choice of parameterization which will make it polynomial. And then we have to take seriously that actually the flow equation is parabolic in the graviton sector too. So in the graviton sector, flows are typically singular towards the UV. And in the conformal sector, flows are typically singular towards the IR. And so actually what we're dealing with is a differential equation which is not classifiable in the partial differential equation literature. It's something which, if you're not careful, is singular in both directions. And the following model suggests that that fixes the couplings down to just 2. Because if you take this differential equation, just the linear differential equation as a model, and you insist that at lambda equals 0, these coefficients here, this potential standing here for the coefficients that you get out, expanding the Einstein-Hilbert action in some representation, if you insist that all of those coefficients have non-singular flows all the way to infinity, then you can show that the higher derivative curvature terms must be singular. That means you can't add the higher derivative terms at the linearized level. They don't have their independent couplings, or at least it's a hint in that direction. Okay, so I think I've caught you up some time. This is my summary page. What I've shown you very briefly is a construction that establishes quantum gravity as a genuine continuum limit in quantum field theory up to order kappa squared, in the sense that you get this standard Wilsonian picture with all the correct properties. It appears to work at each order, but this would require new coupling constants at each order, mimicking what you see in the standard way that you quantize quantum gravity. However, we see hints from this differential equation and the subtleties that go into this differential equation that these couplings could be fixed at the non-perturbative level. And I'll stop there.
Well, thank you very much. Do we have questions? Yes, Andrei first.
Is there any difference between quantum Einstein gravity and other non-renormalizable theories like nonlinear sigma module or Fermi Lagrangian? What is the specific of gravity?
The crucial difference is so much of this is counting on this minus sign. So you have this wrong sign kinetic term for one of the fields. And that's the crucial difference, which is having all of these profound effects on the flow. So the nonlinear sigma model and so on, you wouldn't. You would be told to just quantize that in the usual perturbative way if you tried to quantize it around the Gaussian fixed point.
So in your opinion, that's, how to say, brings about additional difficulties, this wrong sign. That's what you're saying, right?
Yeah, difficulties, but also hopefully opportunities. I mean, there's a world out there that hasn't been explored of these strange differential equations. And as you see, what I ended up with is sort of, unfortunately, not quite there yet, but nevertheless, this is an interesting window into something that hasn't been looked at before.
Okay. Yeah, let me continue with this question. In gauge theory, at least in some gauges, you have similar situations that some of the degrees of some of the fields have a negative sign, A0 has negative sign of the Lagrange, the kinetic term. Is there anything similar happening there?
So I think that's, you're right, of course, A0 has the wrong sign, but that's in Minkowski's signature, where you can then remove A0 by a gauge, choice of gauge. Now, actually, the conformal factor has a similarity in that respect as well, which is that in Minkowski's signature, you can also remove it by a choice of gauge. So you could just say it's a gauge artifact, but you can only do that locally. And here's an interesting point. If you think about the Friedman-Robertson-Walker metric of the universe in conformal time parameterization, you see that the scale factor of the universe is nothing but the conformal factor. So that shows you two things. One, it shows you that actually globally, you can't necessarily set the conformal factor to 0, even in Minkowski's signature. And secondly, that inflation and all of those mysteries are controlled precisely by this field that I'm focusing on.
Not clear. All right, any more questions from the audience or maybe in Zoom? Саша, вы не видите в Zoom вопрос? Все, Ангзар, тебе слово больше не даем. No more questions. Let's thank the team again. Team, thank you very much.
Thank you.
It's great that you finally succeeded to get
Yes.
Yes, thank you.
Thank you.
Thank you
For
very
your
much.
patience.
Так, we come to the last session of today before welcome party. So I give the floor to the chairman.
Thank you. Okay, thank you. So I kindly ask all the speakers to be within the time interval which I have, since we are strongly limited from below by the welcome part. Otherwise, so our next speaker is Professor Andrej Arbuzov from the theoretical laboratory. High precision test at future e-lighters. Please, you have 20 minutes.
Okay, dear colleagues. So my talk is about application of quantum theory, phenomenological applications. So let us discuss the status of the standard model and what we are going to do with it in hopefully near future, but some projects which I will mention will be quite far away. So the outline is a motivation to study the standard model, just a few words about future projects. And the main part will be what we have now in preparation for those high precision studies, what we need. And that is the most important point, what we need. We still have some time, but we should work on it. So we don't have any hint about the energy scale of geophysics. So there is no good motivation to construct a machine of given energy. And even say that, okay, so we try to construct a linear collider for say 5 TeV is a good chance to find something, but finding edges are not convinced. So we are in trouble. We don't know exactly where to look and what to do with the high edges. And to be honest, most likely the running high energy machine, the HC, will not find any in the physics. It is most likely. So, but what it's not the end of the high energy physics at all. we have our physics around us, and that physics is a standard model. And the standard model has many questions inside it. We should study those points, and the most available way to study is do precision tests of it. So we need to measure all parameters precisely, find relations between them and different observables. And as we learned from the history of high-energy physics, we have a kind of interchange of plus and minus and hadronic machines, or sometimes EV colliders. So we discovered Z and W boson as a hadronic machine, and then studied that way. We discovered the Higgs boson at LHC, and then we should study it at future electron-positron collider with high energy. And to do that, we need theoretical predictions, and it is just time to start working hardly on it. We don't have much time because problems are difficult. So, what are projects? Projects of plus and minus colliders are divided into two clients. First are linear colliders, and they can operate at high energies, and then there are circle colliders which are limited because of synchrotron radiation, and the limit is about 350 GeV, but it is a fortunate limit because it is a kind of very interesting energy scale where you have top and top work production. So projects like FCCEE, it is a 100-kilometer circle collider, can be built at CERN. TLEP and another project in China, very similar to XCCE, but it has two main differences. First of all, it can be built like 20 years before XCCE. So time schedule is like this. And it is a bit less precise than XCCE. For XCCE, it's the most advanced project. And all those projects plan to operate at fixed energies with this steps, and those steps are just about the standard model. So the first step is the boson. It is a kind of TerraZ factory which will have enormous amount of Z bosons. Then we have two W boson production, then Higgs-Straun, and then two top quarks. And again, in comparison to linear colliders, luminosity is 2 orders better, and then we can have 4 experiments in a circular collider and only 1 at a linear collider. So here we will do really high precision physics. Just to mention, there is a project of low energies. What we have in the test of the standard model at Lab, we performed quite a lot of measurements of different observables. For instance, a forward-backward asymmetry for big quarks there was some deviation from the general field, but only about sigmas. Yes, and it's at LHC we do some improvements, for instance, in double boson mass, of course, in top quark mass, but not much about other standard model parameters, especially in the electronics. So what do we have now in general? In general, we have a kind of 1.5 loop in QED and electronic for general kind of observables. What do I mean by 1.5? It means complete one loop plus some higher order terms, numerically most important, but only a few results, plus are known into exactly 2 loops. We have quite better situation in PCT, but calculations here are less difficult because of lower number of energy streams. We have some mixed corrections, so electronic, and we have advanced methods. We already discussed at this conference many advanced methods how to do perturbative and even some non-perturbative calculations. What we have already, we have some computer codes which include those results and can include new results. Here I marked projects which I participate, so Z-filter and DZ were programs quite often used at Lebedev, and I also participate now in the project, so with its name of Monte Carlo event generator, which is developed by our group, the SINP group. So this generator is a new one, and it is actually it's done for future CCE on several processes included, and only in this approximation. Okay, that we have. So, just one example. For instance, consider forward-backward asymmetry. It is a quite interesting observable, measured at lab, and certainly will be used at future colliders. So it is sensitive to electronic couplings of electron and final state kernel. So then you can study lepton universality, you can again scrutinize electronic mixing. So it is quite an interesting concept. And we perform numerical calculations. So we consider compare Burt asymmetry with weak QED and combined electronic contributions, and we see some effects. What is more interesting is that we can do that in different electronic schemes. So like in QCD, we can have different schemes, and here we can choose different input parameters, alpha from 0, 1 over 137, alpha from MC, which looks better for measurements that wasn't big, and GPU or GFermi scheme, which uses which computes alpha from the peak from beyond decay. Okay, and scheme dependence result in difference between complete one-loop results and difference. So with this shift of forward asymmetry is visible not only as a picture but numerically is quite important. And what does it mean? It means that what we have now in perturbative calculations is not enough even in a simple calculation. How can we prove? We need complete two-loop results for such observables. I mean, complete peak contributions, QED is known, and there are recent results, for instance, with some exponentiation by Vyacheslav and two-loop for backward asymmetry by this German group. So we have some progress in theory also, but that is certainly not enough. So opportunities at FCC are quite impressive. So here we can see the present values and errors and what can be done at FCC in experimentally. So you see that the error, for instance, for that boson mass can be reduced by 20 times. So this all other error observables are really interesting. So for asymmetry, proper measurement, extremely well. And even the Higgs boson cell coupling, which will not be measured at LHC, one with maybe some plus minus 100%. So it can be measured at FCC with precision of 1/3. Yes. So what we need from theory? From theory to reach to match that experimental precision, we need quite a lot. We need high order calculations, mixed corrections, say alpha square. We need another kind of mixed corrections, high order QED, and at least two-loop periodic contributions. So, and of course, where we can do better, yes, it is good. But most hard points are just big contributions. It is really. But we have some progress. We have some progress, and we have methods. So what to do? What to do? First of all, I start. The studies of the standard model are important regardless any searches for new physics. And only knowing the standard model predictions from the standard model, you can look for the new physics, which is a deviation from the standard. So this collider should be built, regardless again about any new physics. It should be built to study our physics certainly. Theoretical predictions are required, what we have is not enough. And that should be done independently by different groups with comparisons, and this procedure is already started. There is certain self-organization, some workshops are running, and our group does participate in it, in some of them. So we need both Monte Carlo and semi-analytic models. What I mean? Of course, the experimentalists prefer Monte Carlo, and that can be used directly as experimental analysis of experimental data, but semi-analytic models with just for say complete cross sections or some pseudo observables, it is very good to have. First of all, to comparison between different groups, but then to check Monte Carlos, which should be much checked on say something which is more stable numerically. So treatment of high-order electrolytic effects should be improved. It is the main problem to nowadays from my point of view, and there is a progress. For instance, there is a series of works by Iris Riemann, Zhemchugov, Vyacheslav, and some other people who did perform complete two electrolytic calculations, but only for particular energy point, that is most important point, and only for some pseudo observables. We need more. What do we need? Actually, we need to look form factors. By form factors, I mean just coefficients before different Lorentz structures in those processes which will be measured at the future colliders. So it is a kind of request. Some work is already started, but that was I wanted to say. Thank you.
Okay. Please, any questions or comments?
Yes, please.
Please.
Thank you very much for this talk at the cutting edge of experiment and phenomenology. I mean, personally, I rejoice in the fact that the standard model is in so much good state. But I have a question to ask you about the slide where you showed projected theoretical uncertainties. Could you go back to that, please? Projected theory error. Yeah? What is the difference between projected theory and current theory? How much more work do we need to do to get to your projected theory error, and what assumptions are you making about that?
Yes, thank you for this question. And just giving time to describe the detail. But yes, what this projected accuracy means that if we include those corrections which we plan to compute, so mixed alpha s square, mixed alpha square alpha s, alpha cube, then we will have this projected accuracy. And this projected accuracy is comparable, but with the experimental accuracy, sometimes still worse, but what that can be, that is more or less kind of realistic estimate what we can compute. Of course, we can try to be better.
Okay. Thank you.
Thank you.
Thank you very much for the talk. Actually, I have a comment rather. You said that those you need two loop electroweak form factors. So my impression is that multi-loop methods are just grown enough to calculate those. So it's a big amount of work, of course, but it should be doable. Yeah.
I have two comments. The first one related to very first transparency and your statement about the physics at Large Hadron Collider, which in fact, sorry, but you know, I think it's too strong statement, and scientifically, I mean, that is not quite correct. So, yeah, to be honest, most likely, come on, I mean, that is probably for you most likely, but I mean, yeah, thousands of people are working on that, and sorry. Moreover, I don't think it's a good argument for E plus E minus machine, because having this argument in mind, it would be very difficult to convince people to get money for E plus E minus machine. So, I mean, just be careful with such a statement. And so that's, please, no. Okay. Yeah, well, no, well, we should, I mean, saying something scientifically. And scientifically, before we have a chance, we have to look at and try to find something new. So if something is not forbidden, we should look at it. Yeah. Okay, and the second question or comment about linear or E plus E minus machine in general, you are saying precision physics is very important. I fully agree. One should make it precision physics as precise as possible. All computation should be done. But what for? And but in order to answer that question, what for? We have to somehow to mimic, to feel, to compute some deviations from expected deviations from the standard model. And that is what you didn't mention at all. And in order to make it, you need to parameterize perfectly those deviations or somehow in a correct and right way. And that is, okay.
Thank you. So I don't see any more questions or comments.
We should fit in time, actually. We have no time for questions.
That number of neutrinos with high precision is 3, right? By fitting, not 4 and more. But for sure, we know, we have a priori information that the number is 3 in this precision. If we restrict the fit precisely by number 3, what can happen?
Thank you. So I don't think we have any more time for questions or comments. Thank you again. And our next speaker is Professor Igor Volobuev, from Moscow University. And he will speak about neutrino oscillations in quantum field theory and the solar neutrino problem. It will be Zoom.
Thank you very much. Thank you.
Minutes.
Thank you. So first of all, I'm very pleased to have the opportunity to speak at this conference because I've known the Magnificent Seven of theoretical physicists for 50 years. I cordially congratulate them on their anniversary and wish them many new interesting results in the field of quantum field theory. So next, I'm going to talk about neutrino oscillations in quantum field theory. So the standard model, which is a gauge quantum field theory, allows us to describe a great amount of various elementary particle interactions in the framework of the S-matrix formalism and the Feynman diagram technique. However, there is a belief that it cannot describe the phenomena of neutral Kelvin and neutrino oscillations. These phenomena are being studied both theoretically and experimentally nowadays. Unlike the scattering processes, neutrino oscillations occur at macroscopic space and time intervals. And it is a well-known experimentally confirmed phenomena, which is usually understood as a transition from a neutrino flavor state to another neutrino flavor state, depending on the distance traveled. The theory of neutrino oscillations was developed in Dubna and can be found, for example, in this paper by one of the founders of this theory. Nowadays, the standard way to describe the phenomenon is the quantum mechanical approach in terms of plane waves. However, it is inconsistent because the production of the neutrino flavor states is described within the standard model, whereas the evolution is described within quantum mechanics. Such a description is eclectic because quantum field theory includes quantum mechanics as an indispensable part and must be able to describe all quantum phenomena. Moreover, the neutrino flavor states cannot be regarded as true quantum states. That is, states of a quantum system. Really, according to the principle of quantum superposition, only quantum states of the same Hamiltonian, we can take linear superpositions only of states of the same Hamiltonian. However, neutrino mass eigenstates have different Hamiltonians, and we cannot build their quantum superpositions. It results in the fact that the production of such states without definite mass leads to violation of energy momentum conservation. This problem is allegedly solved in the wave packet treatment, although the corresponding calculation of amplitudes are very bulky. Thus, a construction of a consistent and convenient description of neutrino oscillation within quantum field theory is of current interest. The first attempt to describe neutrino oscillation within quantum field theory was made almost 40 years ago in this paper. In this approach, the produced neutrinos are off-shell and are described by Feynman propagators in the coordinate representation. Now, neutrino oscillation is an ordinary interference process. Neutrino flavor states are not needed. In the approach under consideration, the incoming and outgoing leptons were described by plane waves, whereas the positions of nuclei were fixed by delta function, which was a rather rough approximation. As a result, in the momentum representation, there appeared distance-dependent propagators of virtual neutrinos. The idea was developed in the paper by Junte and co-authors, and And in this paper, the localization of the incoming and outgoing particles on nuclei was described with the help of wave packets, which makes the calculation of the amplitudes very complicated. There are many papers which follow this tradition and use wave packets for describing neutrino oscillations within quantum field theory. However, this again results in very complicated calculations. The reason is that the standard S-matrix formalism is not appropriate for describing processes passing in finite distances and lasting finite time intervals. We put forward a modified perturbative formalism, which allows us to describe the processes passing at finite distances during finite time intervals. The approach is based on the Feynman diagram technique in the coordinate representation, supplemented by modified rules of passing to the momentum representation. The modified rules reflect the geometry of neutrino oscillation experiments and lead to a modification of the Feynman propagators of the neutrino mass eigenstates in the momentum representation. The idea comes from the famous paper by Feynman, and it was developed in our papers, in these papers. I would like to remind you that the modern perturbative S-matrix formalism and the diagram technique were formulated in the papers by Dyson and Feynman back in 1949. Although the paper by Dyson appeared first, the results of Feynman were already known at that time. The paper by Dyson is a formal mathematical construction of S-matrix, but the paper by Feynman is a rather intuitive physical space-time approach to describing processes within quantum field theory. So a standard scattering process takes place in a finite space-time volume. And according to Feynman, the events, the production, the interaction events lie within this space-time volume, and the propagation of particles between these events is described by Feynman propagator. To obtain the amplitude of the process, we have to integrate over the amplitude over the space-time volume. However, if it's finite, it's almost impossible to carry out these calculations. So to simplify calculations, we blow up this volume to Minkowski space. And as a result, we obtain S-matrix rules for calculating matrix elements. Thus, S-matrix is a formalization of this physically rigorous perturbative description of scattering processes. Let's look at the situation with scattering processes in neutrino oscillation experiment setting. The situation is quite different. In this case, we have two space-time regions. In one region, neutrinos are produced, and in the other region, they are detected. And the propagation of neutrinos from the production to detection point is described again by Feynman propagators. To calculate, again, according to the logic of Feynman, we have to integrate this elementary amplitude over the space-time volume of production and space-time volume of detection. And again, it's a very complicated problem. We suggest that we do the same as in the case of S-matrix. We blow up the production and the detection volumes to Minkowski space, but we keep the distance between the production and detection points fixed. This can be achieved by introducing the delta function into the integrand of the amplitude. Formally, this is equivalent to replacing the standard fermion propagator by this propagator multiplied by this delta function. So the vector n is the direction from the center of source to the center of a detector. And the transform of this product is called the distance-dependent fermion propagator in the momentum representation. It looks like this, and the integral can be evaluated exactly. The expression is rather complicated, but when we consider oscillation processes, the detection and production processes are separated by a macroscopic distance. It means that the neutrinos propagating, virtual neutrinos propagating at macroscopic distances are almost on the mesh shell. And for such particles, this relation is valid, and the propagator can be approximately reduced to this very simple form, which will be used, we will use in our calculations. We work in the minimal extension of the standard model by the right neutrino singlets. The weak interaction Lagrangian is of leptons is standard, and we also use the one-dimensional approximation where the neutrino momenta are assumed to be directed from the center of a source to the center of a detector. It's the standard approximation in the theory of neutrino oscillations. Let's first consider processes where neutrinos are produced and detected in charge current interaction with nuclei. So the corresponding diagram looks like this. This field circles stay for matrix elements of the weak hadron current between the initial and final states of nuclei. The amplitude corresponding to this diagram can be written out exactly like in the standard Feynman diagram technique. We should just replace the propagators by the distance-dependent propagators that I have introduced. And then we have to calculate, we calculate the amplitude in the Fermi approximation, in the approximation of Fermi interaction. And it turns out that the squared amplitude summed over the particle polarization factorizes in the approximation of massless neutrinos. So we get the squared amplitude of the production process, the squared amplitude of the detection process, and this oscillating factor. When we integrate over the particle momentum, we get that the probability, that the differential probability of the process is the differential probability of the production process, the probability of the detection process, and the standard oscillating factor. To find the probability of the process, we have to integrate with respect to the magnitude of the neutrino momentum, because the experimental setting determines only the direction of the neutrino momentum, but not its length. Similar formulas can be obtained for processes where neutrinos are produced and detected in both charge and neutral current interaction with electrons. We can also describe processes in external magnetic field, where the distance-dependent propagator depends on an external magnetic field and looks like that.
You get 5 minutes.
Thank you. We have applied this formulism to describing solar neutrinos. So here are the experimental results which show the measured neutrino flux and the ratio of the measured neutrino flux, the ratio of the measured neutrino flux to the neutrino flux predicted by the standard solar model. With our technique, we can get expressions for the probability of neutrino, asymptotic values of the probability of neutrino oscillations. It turns out that the processes, that the oscillations depending on the neutrino momentum vanish at large distances, and only the asymptotic value remains. It looks like that. So this is the asymptotic value in vacuum, and when neutrinos come to the convective zone, there are new oscillations due to the magnetic field in this zone, and this is the final asymptotics. We have calculated the value of this final asymptotics depending on this product mu0 to h. This is mu0. It is the ratio of the neutrino magnetic moment to the neutrino mass, and this line is the minimal experimental value admissible. So we see that there are many values of this product which are compatible with the experimental data. So I come to the conclusion. We have developed a new perturbative formalism which allows one to consistently describe neutrino oscillation within the standard model without use of neutrino flavored states. It has also shown that the magnetic field, the energy dependent oscillation of solar neutrinos cannot be visible on Earth. Only the energy dependent oscillations averaged is observable, which can be a part of the solution to the solar neutrino problem. So thank you very much.
Your cross sections depend exclusively on the distance.
It's I cannot hear you. There's something wrong with the microphone.
Of sign, your cross section depends on the distance between source and
exactly.
detector. For small argument, the sign. You have linear dependence on the distance, right? So derivative.
No, it's not linear. It's not linear. It's the standard. Look, it's the standard oscillation formula.
Square dependent on the L. So you can, for rather small, correspondingly small L, measure that contribution, right? It's the effect of your scheme. And by this experiment, you just change this distance. You can measure the mass square difference. Is it a right proposal for the experiment from that model?
Well, you see, one can measure the neutrino mass difference in experiments with neutrinos produced at colliders. But we've considered here only solar neutrinos. And if we consider solar neutrinos, this distance dependent, this energy dependent oscillations fade out at large distances. So we cannot observe them on Earth. But if we consider neutrinos produced at colliders, of course, we can measure the dependence of these probabilities on the distance, and we can estimate the neutrino method. It's the standard approach. In fact, our formulas for this case coincide with the standard ones.
Thank you. Okay, I don't have a question. So I don't see any questions anymore. So thank you again, Igor Volobuev.
Thank you.
And our next speaker is Evgenii Zhemchugov from Moscow Lebedev Physical Institute. Ultraperipheral proton-proton collisions at the LHC survival factor. Please, 20 minutes.
Hello. Thank you to the organizer for giving me the opportunity to give the talk. Is it working? Да. Чем переключать? Чем показывать? So my talk is about ultraperipheral proton-proton collisions at the Large Hadron Collider survival factor. Here's a short summary. I will consider ultraperipheral collisions, and I will discuss equivalent photons approximation in the case of proton-proton collisions. First, I will assume that the colliding particles, the protons, do not interact strongly. They interact only through electromagnetism. This is actually a surprisingly good assumption in the case of protons, as long as we talk about production of a system with invariant mass smaller than the proton Binding energy times the proton Lorentz factor, which is about 1.40 V in the current LHC energies. Then I will relieve the assumption and introduce the survival factor as a ratio of the cross sections of the process does not take into account non-electromagnetic interactions to the cross-section of the process that does so. And then I will consider production of a pair of heavy charged particles and compare it to the Atlas experiment where the pair of muons, which are not heavy, but that's all we have now, has been measured. In a large fraction of collisions at the LHC, colliding particles do not collide head-on. They rather pass at some distance from each other and collide with their electromagnetic fields. If the particles survive in such a collision, this is called ultraperipheral. And here is a Feynman diagram of a typical ultraperipheral collision. We have, in the initial state, we have some charged particles, either protons or, for example, lead ions. They both emit a photon, and these photons fuse to produce some new system, and the initial particles go to the final state. They don't lose too much energy, so they usually fly out of the central detector. But in the case of protons, they can be detected by special purpose forward detectors located at about several hundred meters further down the stream. So we have a very clean event. We have final state. In the final state, we have the two initial particles and whatever has been produced in the fusion of photons. And in the case of protons, we can actually reconstruct both the transversal and longitudinal momentum components of the produced system. Now consider a charged particle at rest. It is surrounded by an electric field, which can be represented as a bunch of virtual photons with zero energy component and some spatial components. When we change to the reference frame where the particle is moving with the Lorentz factor gamma very large, the photons acquire energy, which is approximately equal to the longitudinal component of the photon momentum, and the transversal components do not change. So we have proton virtuality, which is minus square of the photon momentum, is much less than the photon energy. So these photons are approximately real, and in this sense, the large hadron collider can actually be considered as a photon-photon collider. Equivalent photon approximation states that the photons are exactly real and distributed according to some spectrum n. So we consider collision of two particles A and B. They survive. So we can change from considering this reaction, considering this reaction, where the photons are real and distributed according to some spectrum. Cross-section of the ultraperipheral collision is then the cross-section of photon-photon collision integrated over the photon spectra over all energies. The expression for the spectrum is provided here. Z is the charge of the collision particle of the source particle. So, for example, in lead ions, this is proportional to Z to the fourth power, which is a very large number. So lead ions are very attractive in the case of ultraperipheral collisions. But here we talk about protons, so Z is just equal to 1. F is perpendicular is the photon transverse momentum, so it's composed of these components which do not change when we boost the particle. And F is a direct form factor. The role of the form factor is that it cuts off the integration at high energies. For example, if we consider a proton, when it is a photon of energy too high, it breaks apart. It can break apart. So this is taken into account with the help of the direct form factor. Proton form factor is usually represented as a sum of so-called Zaks form factor, which is the electron form factor and magnetic form factor. Photon energy is limited by the breaking energy of the photon of the proton in its reference frame. So photon virtuality is actually limited by approximately proton median energy squared, which is lambda QCD squared. So it's about 0.04 GeV. So we get that in interperipheral collision, the important region is when tau is much less than 1. So usually the contribution from the magnetic form factor can be neglected. But we found that its contribution is actually on the same scale as the survival factor. So we had to keep it in our calculation. Here are the formulas for the dipole approximation of the form factors, where mu p is a proton magnetic moment. And lambda is some numerical parameter which old books actually quote to be equal to lambda squared is equal to 0.71 GeV squared. We actually couldn't find any reference to this value. No paper can be quoted for this value. And recent experiments actually disfavor dipole approximation altogether. So here is plots from the paper of A1 collaboration, which is based on the Mainz experiment. Here is a Q squared from 0 to 1 GeV squared, and here is from 0 to 0.2 GeV squared. Here is a ratio of the measured electron form factor to standard dipole form factor. Here it is the same, but on a larger scale, and here is the proton magnetic moment times measured electron form factor divided by measured magnetic form factor. So, as I said, we are mostly interested in the region where Q squared is less than lambda QCD squared. So this is very short region here. Points are values obtained by previous measurements, and the shaded region is the results of the fit of the A1 collaboration based on the Mainz experiment. So we are only interested in the small region here, and it is related to the the derivative of the form factor at 0 is related to the proton radius, which has been measured in the same experiment. And for this ratio, we got that we can actually try to use the dipole approximation with lambda squared equal to 0.61 GeV squared. Just a little correction. This summer, Data Collaboration has published a new result on the measurement of proton radius. They apparently have taken into account measurements of muon hydrogen atoms, and they got 0.84 femtometers here. So in this case, lambda squared is 0.67 GeV squared, and our results will be about 2% higher than I will show today. So we took the dipole approximation of the form factor and plugged it into the expression of the EPA spectrum. And we got this very large and ugly formula with blue parts coming from the magnetic moment, magnetic form factor. The black parts of this formula were previously published, but the blue part, I think, is our new genuine result, which hasn't been published previously. In this formula, we can the cross-section of photon-photon production depends on just a product of photon energies. So we can be a little simplified if we change to different integration variables. If we take S and Y, where square root of S is the invariant mass of the system produced, not the proton-proton collision energy, we use this notation here. And Y is the rapidity of the system produced. We get this formula where the quantity is the photon-photon luminosity, and it is expressed as the integral of photon spectra coming from both particles. So up until now, I did not take into account the possibility that protons can interact strongly or some other ways, but electromagnetically. To take it into account, we need to introduce the impact parameter. So we are considering now the collision in the space, in the plane perpendicular to proton momenta. And we consider a photon spectrum at a given point in this plane. Our old spectrum, which is one variable, is now the integral of the two variable spectrum over the whole plane. And the expression for the spectrum is given here. Here, J1 is the Bessel function. And the cross-section for the ultraperipheral collision is now the integral of the photon-photon cross-section over a whole spectrum, over a whole plane twice, and over all possible photon energies, weighted with the probability that the protons survive in the collision with the impact parameter B. In this case, equivalent photons become polarized, actually. So if we consider them in a particular point in space, the polarization vector are collinear with the radius vector from the source particle. So we have to take into account the polarization. Cross-section, we get here a cross-section with parallel polarization and cross-section with perpendicular polarization times the corresponding luminosities. The luminosities are written here. They differ only in the last term, and if we neglect non-electromagnetic interactions, in this case, the probability is equal to 1, and we get the integral of cosine squared phi from 0 to 2 pi, which is equal to the same integral of sine squared. So luminosities in this case are equal, and we get that the cross-section is the cross-section for ultraperipheral collisions depends only on the average of the polarizations. So now we can define the survival factor as the ratio of the cross-section where we take into account non-electromagnetic interactions to the cross-section where we don't take into account non-electromagnetic interactions. Here it is written. If we neglect photon polarizations, we can move out this cross-section out. This cross-section out of the integral over impact plane, and we can write we can define the survival factor as a ratio of the integrated function. So it will be the ratio of luminosities, which depends on either on photon energies or photon the invariant mass the system produced and its rapidity. And I will, in the following, show plots for several factors defined as integrated luminosities over rapidities in the numerator and denominator. So again, we took the cross-section, took the dipole approximation for the proton moment form factor, plugged it into the spectrum, and got this formula where blue parts are again our new result. In the case of PP collisions, there is this empirical formula which describes the probability that the protons do not interact strongly. So we plug it into the expression for the luminosities, and again we get quite big formula, but it is calculable. Here is a survival factor. The colored lines are luminosities. They are plotted with the left axis, and the black line is the survival factor. It is plotted with the right axis. The red line is the luminosities where we do not take into account non-electromagnetic interactions. Blue line is where we do take into account non-electromagnetic interactions, and the black line is the ratio of these two luminosities. Green and magenta lines are luminosities for specific polarizations. As you can see, the difference is very small, so probably in most cases, photopolarizations can be neglected. Now, if we consider a particular process, which is production of a pair of charged particles, the production is described by Breit-Wheeler cross-sections, but I shall not stop here. And here is a calculation of the cross-section for the production of a particle with given mass from 90 to 250 GeV. Again, we get red line is the cross-section, and is the colored lines are the cross sections, and they use the left axis, and the black lines are ratio of the cross sections. They use the right axis. The dashed line is when we neglect the photon polarizations. In this case, the cross section will be done indistinguishable from the blue line. So in this plot, so again, addition of taking into account photon polarization reduces the result very small, less than 1%. To compare to the experiment, we need to calculate a fiducial cross-section. We consider the usual LHC cuts on the transverse momentum of the produced particles and the rapidity of the produced particle. Again, I don't want to go into details here. The message to take home is that it mostly can be done analytically with just numerical integration required to calculate the final value. Here, the cut on transverse momentum is taken into account by this integral limits, and the cut on pure rapidity is taken into account by these limits on rapidity. And here is our comparison to the experiment. So Atlas has measured cross-section of the production of muon pair in ultraperipheral collision for protons colliding at 13 TeV, and the blue line is the lines are the differential cross section. Here there is a drop which is related to the change in the cut on muon transverse momentum. Points are experimental data, and histograms are corresponding lines integrated over the same bins as the experimental data. Red line is when we do not take into account non-electromagnetic interactions, and blue line is when we do take into account non-electromagnetic interactions. The bottom plot is the ratio of our calculations to the experimental data. So we get when we do not take into account non-electromagnetic interactions, we get 3.39 picobarams, and we do take into account, we get 3.26 picobarams. While the experiment is 3.12 plus or minus about 0.17 approximately. So we get a better agreement with the experiment if we calculate, take into account the survival factor. So my conclusions is that ultraperipheral collision is a way to study photon collisions in the LHC. They actually have considered quite a several processes. For example, recently they have been measured cross-section of light by light scattering, which was very interesting result. With equivalent photon approximation, many calculations can be performed analytically. Numerical integration is required, but Monte Carlo simulation is not required. So usually it can be done faster. Well, at least until, unless you take into account the survival factor, it can be done faster, but with survival factor, it takes quite a lot of time to integrate. Survival factor and photon luminosities in proton-proton collision were calculated for invariant mass up to 3 TeV. So I hope that given our survival factor calculations, you can just calculate using more faster method, neglecting photon polarizations, neglecting the non-electromagnetic interactions, and just multiply by our survival factor and get somewhat good estimate. We are in good agreement with the Atlas experiment, and I'm currently working on publishing our code at GitHub in the library, so perhaps you can use it in your calculations if you are interested. Thank you for your attention.
Thank you.
I have a question or more remark. I'm wondering about your choice of form factors because you have equal energy dependence for electric and magnetic, while the Jefferson lab sees something quite different. So it might be a suggestion to use to verify form factor choice.
We actually have calculated with the form factor provided the A1 calibration in numerical form. It is only given from 0 to 1 GeV squared, and it actually has very large uncertainty in this region. What? Mines, yes. Oh, thank you. Yeah, this is a good comment. We will check it.
Okay, thank you.
So, David, are you going to ask a question?
Yes, please.
Yes.
Thank you for this talk related so much to experiment. My question concerns your comments about numerical integration and Monte Carlo simulation. Can you tell me the dimensionality of your numerical integrations?
Yeah, this is a very good question. Thank you for asking it. So here we have two expressions for the cross-section. The below one is when we take into account non-electromagnetic interactions. So we have to calculate the survival factor. And here, as you can see, we have, well, here are 6 dimensions, but one dimension is trivially calculated. So it's a 5-dimensional integral. And in the top plot, in the top part, we have when we do not take into account electromagnetic interaction, it is 2-dimensional integral. So yes, the bottom integral calculates a long time, but it all depends. I still think that it is faster than Monte Carlo simulation. At my work computer, I calculated 1,000 points in like 10 hours, I think, for the bottom. For this plot with the fiducial cross-section also taking into account. Yeah, by the way, when you want to take into account fiducial cross-section, you add another integration over PT. So it's 6-dimensional and 3-dimensional.
Thank you.
Can I ask a question? Are you aware of paper by Raka, Julia Raka, in 1937, I think? He calculated the same thing, but without form factors. Have you compared your result with his formulas?
I remember I was reading this paper, but I don't actually remember exactly what it is about. There was a paper by Khan, who calculated same thing for lead ions, also at the time. And yeah, they did not take into account the form factors, so the calculation was a bit easier. The primary difference is in spectrum. For when the form factor is not taken, yeah, when the form factor is 1 for point-light particle, it's easier, but otherwise it's similar.
Okay, I think we have time for questions. So thank you. Thank you again. And our next speaker is Dr. Sergey Goloskokov. Dr. Sergey Goloskokov, general particle distributions in exclusive meson production from Dubna Institute. Please, 20 minutes.
Так. Okay, I will speak about general parton distribution in exclusive meson production. I will discuss properties of GPDs and how we can model them, amplitudes of meson production in terms of GPD, some physical observables, and all this connected with leading twist contribution. And it will be shown that at pseudo-scalar meson production, leading twist contribution is not enough, and we consider twist-3 transversity effects, which are very essential there. About GPDs, when we compare deep inelastic scattering, which is cross-section of this scattering expressed in terms of ordinary parton distribution, and compare this contribution with deeply virtual Compton scattering, when we have different moment here photon is virtual, and this we have real photon. Here we can have momentum transfer. In this case, we have non-symmetric distribution, and generalized or generalization of ordinary parton distribution was proposed in this sense by Radyushkin and G. And Radyushkin, together with our colleagues, celebrate during this conference his 70 years. And I congratulate all our colleagues. So in more details, when we look at these graphs, it was shown by Radyushkin and G that it can be factorized at this generalized parton distribution, which depend on 3 variables at usual x, xc, difference between this moment, so-called skewedness, momentum transfer. So we have 3 variables here, and the factorization for this process was shown, and the same factorization was shown for meson production. And this hard scattering part here can be calculated perturbatively, and GPDs are universal functions which are the same for different processes like ordinary PDFs. We can see that generalized parton distribution at in the forward limit at 0 skewedness and momentum transfer is equivalent to ordinary parton distribution. It was shown by the same authors that
hadron form factors are connected with GPDs through the moments. And in addition, information about parton angular momentum can be calculated using G-sum rules. So we see that GPD contains very extensive information about hadron structure. Now, how we can model generalized parton distribution? By Radyushkin, it was proposed so-called double distribution representation, which connect generalized parton distribution with the ordinary parton distribution through this double integration. And for ordinary parton distribution, we use CTEC parameterization together with Regge-like form. As I said, we can calculate amplitude of meson production as a convolution of generalized parton distribution and some hard scattering path which calculated perturbatively. For generalized parton distribution, we use double distribution representation together with CTEC 6 function. What about hard scattering amplitude? The hard scattering amplitude is represented as some integral which contain meson wave function, Sudakov factor here, and which connect gluonic radiative corrections here. And in the quark loop here, we consider some K-square over Q-square corrections. This is can be regarded as an effective consideration of non-leading contribution. Now we have all to calculate physical observables. And in this graph, I show cross-section of raw meson production and 5 meson production, the Q-square dependence. And this line represent the leading twist correction without this K-square divided by Q-square corrections. We see that these corrections are very important at low Q-squared, and this factor can be about 10 here. Now, W dependence, you see that we represent properly experimental data at for 5 meson production from low energy, but for raw meson production higher than 5 GV squared. Here we have some growth which do not explain by the model, and we don't know how to explain it. Maybe low energy resonances or something else. Now, a few words about AUT asymmetry. AUT asymmetry expressed as a term of interference of E and H DPD divided by H square. And you can see that we reproduce properly experimental data from Hermes and Compass. Of course, experimental errors are quite large, but we don't have any more. But it can be shown that this leading twist contribution is not enough at low Q squared, at least for pseudo-scalar meson production. If we consider such asymmetry, we can see that this asymmetry is very high, but this asymmetry is proportional to interference of this 0 minus plus plus amplitude and spin on flip amplitude. if we calculate this amplitude in our approach, we obtain very small values, and this asymmetry will be about 0. But we see that this asymmetry in this case about 50%. We solve this problem by calculated twist-tree amplitude with transversity GPDs. We calculate two amplitudes with minus polarization here and plus polarization here, and zero polarization because this is a pseudoscalar meson. In this case, we found that we have the same hard scattering path, but here we have H transverse and this E transverse GPDs. In calculated of this this path, we take into account this three meson wave function. This transversity GPDs at zero skewness and momentum transfer is equal to usual transversity proposed by Anselmina, and this GPD is not well known, and we know this some information of this GPD only from latest results. And using these results, we calculate this amplitude and calculate cross-section. What we found, we see that we have result by this, and this experimental data was appeared after our calculation. What we see here, first of all, that we have correlation between this cross-section and transverse cross-section. And longitudinal transverse cross-section is very small, and longitudinal cross-section, which is leading twist, about this cross-section. So we predict that in this case, we have very large contribution of transversity effects, which very large with respect to leading twist contribution. Of course, this figure is not cannot directly show that this explanation is correct, but 1 year before there was experiment from hall A at Fermilab, where there was separation longitudinal and transverse cross-section. And you can see that here you have transverse cross-section, which very close to our model, and longitudinal cross-section is very small. But this experiment was done at very low Q squared, yeah, about 1.5 GeV, and a few months before, there was the new experiment of the same group where they study longitudinal and transverse cross-section at much higher Q squared, about 6 GeV, and result was the same. So they conclude that even at 6 GeV, we are far from asymptotic regime. So I'm going to conclusion. We show that generalized Spartan distribution with double distribution form proposed by Radyushkin can be successfully used in to study exclusive meson production. We describe properly rho and phi meson production. We found that the leading twist contribution is not enough for low energy P0 production, and the essential contribution here is connected with transversity effects. That's all.
Thank you. Okay, are there any questions, please?
What is the difference between generalized partial distribution functions and unintegrated partial distribution functions? How do they relate?
It's more or less similar, but there are some
we can discuss. Okay.
So any more questions or comments? I don't see any. No, over Zoom.
No. Any questions from Zoom?
Right, then, thank you, Sergey, again. And our last speaker is Vyacheslav Spiridonov from a theory laboratory of the GINR Institute. Please, 20 minutes.
That's okay. Here's my slide. So good evening, everybody. Sorry to keep your time. It's very late, but it's not my fault. I had to speak so late. It was quite interesting conference, as you see, that's the reason. Okay, what I'm going to tell first, the two aims. First aim is to congratulate these 7 great scientists with special greetings to Kostya Chityrkin, who was my PhD supervisor, and to Dima Kazakov, with whom I'm working shoulder to shoulder now more than 25 years in this laboratory. So special greetings to them. What I'm going to talk about is about the interplay between 4 dimensions and 2 dimensions. You know, several cases, at least they were presented already during today, that 4-dimensional theories, quantum field theories, sometimes reduced to 2-dimensional theories in the sense that some particular dynamics is described by 2-dimensional theories. And 2-dimensional theories, as you know, are very well tied to integrable systems. Many 2-dimensional quantum field theories are integrable. And I would like to present the case when this happens at a different place. One more example. Okay, I start with the definition of super-conformal index, which was introduced by Romelsberger and Kinimin, Vallam, and Raju in 2005, and goes as follows. Let's take 4-dimensional flat super-conformal field theory, and the symmetry group is a space-time group times gauge group times layer group, and the space-time group is very big. And here are the generators, Lorentz rotations, Rupert translations, special conformal transformations to superpartners, some dilatations, and R charge, which rotates the supercharges. And the algebra is very complicated. And if you look at this relation, if you look at this, again, something is, it's okay. If you look at this relation, which is, no, sorry, I cannot find the dot. Where is the dot? Oh, no. No, but I can shift. How to make it small? Okay. So, okay, one more down. Anti-commutator of QQ Dagger is equal to 2H. Normally, it's interpreted as a square root supercharge is the Hamiltonian. In this case, it's not so. The square root of Q, or with this QQ Dagger anti-commutator, is equal to curled H, which is the combination of H, J3, which is part of the rotation, Lorentz rotations, and some R charge with some coefficient. And these QQ Dagger are actually the standard supersymmetry transformation generator Q1, say, and its superconformal partner. So it's different from the standard case. It's different, superconformal piece. That's exactly what you need to use to define the superconformal indices. So here it is. Here's the definition. So you take trace over gauge group. Also, this is G means that you average over gauge group of the following object, -1 in the power of fermions. This is the definition of the Witten index, of course, but these pieces are more complicated. You take parameters P, Q, Y, K, and exponential of minus beta, and put into the powers of that the most general, the full set of Cartan generators, which commute with this QQ Dagger. So R curled, J3, FK are generators of corresponding special combination are curled of 2 charges. And J3 is again Lorentz rotation, a piece of that, and FK is the generators of flavor group, and H is the same. So all these operators commute with the QQ Dagger, and that's exactly what you need. So you need to preserve supersymmetry, one supersymmetry in this huge supersymmetric theory. And then you define this trace. This is complicated path integral, you have to compute it. And the point is that this is the topological object. It describes the space of BPS states. And so in this sector, exactly what you get, these two-dimensional dynamics. And so I will show how from this object, the integrable systems emerge. Okay. First thing, this was flat space and it's bad divergences and so on, and people do the compactification. So they pass to four-dimensional space-time, which is S3 times S1. And actually, it is for this space-time that you compute this path integral, and you evidently only these states contribute to this path integral. And the point is that the isometry of the space-time is exactly corresponds to the chosen those generators are curled and J3 and other FKs. This supersymmetry preserves those generators. Therefore, the definition of superconformal index is preserved. It works in this space-time as well. And now about the computation. Physicists computed formally those people who introduced this object and got the following formula. So this path integral, four-dimensional path integral, is reduced to finite matrix integral, where you have Haar measure of finite over the gauge group of the following exponential. This is essentially the partition function of some statistical sum. And this function index, it's one particle index, is called one particle index, has the following form. What you have here, some combinations, cute combinations of this group parameters PQ, which we introduced, and characters of the fields, of the representations which you work with in this your field theory. This is the contribution of gluons and gluinos, so gauge fields contribution. These are matter fields contributions. So this is essentially the character of the chiral fields which you enter into the theory, which you use in the theory. And this is the conjugate because it goes in conjugation. That's the answer. And you see, this is already finite dimensional integral. And if you plug in into that exact definition of the Haar measure, work out all these contributions, exponentials for particular choice of the field content, you will get a precise definition, exact definition of the superconformal index. What's that? Here it is. Robesberger in 2007 put a conjecture that this topological object should coincide for Seiberg dual theory. So there are four-dimensional theories, minimal supersymmetry n equal 1 in 4 dimensions, and they're connected to each other through the electromagnetic duality. And the conjecture was that the superconformal indices of these electric and magnetic theories must coincide. And here is the simplest Seiberg duality, the example of that. You take four-dimensional theory with gauge group SU2 and flavor group SU6 with two fields. Superfield, which is the adjoint, of course, in gauge field, and here's the character of that. And one chiral field, which is a fundamental representation of both G and F, SU6. Here is the character with respect to the gauge group, and here is the character with respect to the flavor group with the following relation. You note that the characters for the SUN group must satisfy this relation. This is the determinant of intermatrix equals to 1. And this is electric theory, interacting non-abelian gauge theory in 4 dimensions. And the magnetic theory is a confined theory. There is no gauge fields, so you have confinement. And it consists of the free fields of Vesuvian-type field, which is the antisymmetric representation, second rank tensor, with respect to the same flavor group SU6. And here is its character. And what I didn't mention that R charges here is 1/3, here is 2/3 of this field. So these theories must be dual, and how it works at the level of superconformal indices in the following way. So you start from a Haar measure. Here's the definition. It shows up the van der Monde determinant. Then if you slightly renormalize your character variables for these variables entering the definitions, so that now this unitarity conditions becomes of this following form, then here is the explicit expression for this superconformal indices. Electric index is equal to, so these are infinite products, as you see, two bases, P and Q, enter in this way, integral over unit circle with positive orientation. In the numerator, you have 12 elliptic gamma functions. Here is the definition of the elliptic gamma function. And we have 12 them, plus minus means that we separately take elliptic gamma functions. And the denominator, you have 2 elliptic gamma functions. So evidently, this is the contributions of gluons and gluinos. And this is the contribution of the chiral superfields. So everything is very transparent from the quantum field theory point of view. It's just the contribution of these fields into the topological index for these theories. And here is the compact notation. And if you repeat the same story for the magnetic theory, you will get the following very simple expression. It's triangular product of elliptic gamma functions with some simple products. No, of course, any integrations, because there is no integral. It's confinement theory. And so this was done by Dolan and Osborne in 2008, that they gave these explicit expressions for the superconformal indices. And so they proved the conjecture by Rommelsberger that these indices coincide. So how they did it? They have found my paper from 2000. And I proved the theorem mathematically rigorously and published in a mathematical journal that the electric index is equal to magnetic index. So it's a completely different end of the story, because I have a completely different motivation. Namely, my motivation came from these integrable systems, and more, even lower, from I was hunting for exactly solvable cases of quantum mechanical problems. I was looking for new special functions, starting to find the most general one, which can be treated in a closed form. And that's what I have found. And in 2000, I proved this relation as the most general form of the what is known as the Euler's bit integral. This is very well known in physics, in quantum field theory relation. It's bit integral. It works for one loop finite integrals perfectly well. And what I proved, it's elliptic version of this at the very, very high level, because at the intermediate levels you have many cases, and that's that's why I call it elliptic bit integral. And now, since I had this many integrals of such type and mathematical relations for them, how it works at the level of superconformal indices. Here is the elliptic analog of the Euler-Gauss hypergeometric function. Instead of 6 parameters, you have 8. And your now relation is more complicated, second power for products. And this is the, I would say, classical special functions. Special function, you have symmetry relation for that, which is related to the exceptional root system E7. Here, it can be written in the following way. And it describes the Zyber duality for more complicated theories for SU2 gauge group, but now flavor group SU8. And both theories, electric and magnetic theories, are interacting field theories. And this is the electric theory with the superconformals. And this is the magnetic theory. And what is this? This is the contribution of so-called meson fields, which emerge at the dual magnetic case. And so this is also my theorem in 2003, and it proves this Zyber duality at the topological sector for this case. What is nice, there is, of course, elliptic analog of the hypergeometric equation, which has the following form. It's second order Q difference equation with the coefficients of this form, where thetas are Jacobi theta functions. And this is up to now the most general second order difference equation, which can be solved in closed form. And it describes the superconformal index for these quantum field theories. Here is the definition of a short Jacobi theta function. Okay, what can we do with that for this for integrable systems? It goes to n-body quantum mechanical integrable systems of the Calogero-Moser type, Sutherland, and then goes the extension by Rusinars to the finite difference equations. And the most general model of such type is the Van Degen model. And it goes as follows. The Hamiltonian has the following form. It's n is the number of particles. T's are Q-shift operators. And essentially, this is a relativistic extension of those standard Calogero-Moser type models. And potentials have the complicated combinations of theta functions. And the point is that here we look for the eigenvalue problem of this type. And for n equal 1, it has the following form. And as I observed already a long time ago, for very special choice of the eigenvalue and some restriction on the parameters, this is exactly the elliptic hypergeometric equation. So essentially, the superconformal index of those complicated four-dimensional theories emerge as wave functions of the elliptic Rusinars type models. And that was my idea. I was conjecturing that using this relation, and because there are very many integrals of such type of the elliptic hypergeometric type, that there are actually many integral models of this type of the elliptic Rusinars type, and it did appear to be true. I was not able to find them at that time, but later through this superconformal index technique, these people have found the generalization, so they can give you the commuting difference operator. So this line of approaches to the integral system through superconformal indices works perfectly well. the latest work, I have to say something new about, not just give the survey. So in this year, we did with Gor Sarkisyan a work with the degeneration of this V function, okay, thank you, to the level of what is called complex hypergeometric functions. And it goes as follows. First, you remove your parameters, so P, Q, T, and the integration variable. You parameterize in a very special way, essentially when both P and Q goes to 1 and this goes to 1, so V goes to 0 in the exponentials. This is first step called hyperbolic degeneration, and then you see there emerges two quasi-periods, omega 1, omega 2, and here's a very cute quantization when they are equal to each other up to sign. If delta goes to 0, then you parameterize your complex variables entering these functions as sum of integer plus some vanishing complex variable, and take the limit delta goes to 0. This is very cute. In the two-dimensional conformal field theory, it corresponds to the case B goes to I, which corresponds to central charge going to 1, I guess. And 0, 1, yes, but the opposite is 25. So it's related to special conformal field theory in 2 dimensions. And what happens? It happens that this finite difference equation in one variable becomes the finite difference equation in 2 variables, namely in discrete variable n is integer, this n is integer, in this n is also integer, and finite difference equation in u. So this is the degeneration. And the point is that this is, as I said, can be interpreted as a special case of this n-dimensional integral model, n-body model for n equal 1. And just interpreting such equation as the degeneration of those of one division model, we have found that one missed point in integrable systems. Clearly, people missed one rational type of models in Kalogjero-Sutherland type things. When you consider relativistic models of such type, there is a special regime when you work with the combination of such combination. You see your variables are integer plus some purely imaginary case variable. If you parameterize variables in this way, there appears a special measure which allows you to build models with, so these are physical variables now. M is integer, which is conformal spin, which takes arbitrary integer value, and U is some complex parameter, standard continuous variable in this rational model. So we have found new set of integral models, which were missed by all this community in the context. And the solution of this equation is given by so-called complex hypergeometric function, which I will not describe. This is quantum mechanical model. Yes, I'm talking about n-body Kalogjero-Sutherland type model. Okay. With whom? So essentially, you start from Rusinars or Bandesian and take rational degeneration. The difference is that they consider, no, it's okay. They consider only one variable case. We have 2 variable cases, one integer, one continuous. And the point is that their measure is given by standard hypergeometric integrals. Here we have complex hypergeometric integrals.
In Rusinars, there are arbitrary many variables, as much as you want.
No. I mean the physical variables, coordinates of the particles, if you will. And here you have coordinates of the particle continuous and discrete. So discrete part appears, which has interpretation, for instance, as a conformal spin. And it takes
it's not spin Rusinars, yeah? It's different.
No. It has nothing to do with spin Rusinars. Okay, thank you for the question because it clarifies the things. And finally, I will skip the definition of the elliptic Fourier transformation, which emerged in this way. It's related to the star triangle relation, which is, of course, a member of the quantum integrable systems. So what I want to say is that elliptic Fourier transformation defined by this formula leads to the operator star triangle relation as the operator form of the same elliptic beta integral. Jointly with Derkachov, we used that to rewrite this this star triangle relation as the Coxeter relations for some particular integral operators emerging in this way, and gave the solution of the standard Yang-Baxter equation as the integral operator as a combination of these operators. I skip this because the next slide is much more interesting. So in relation to 2-dimensional models of the Ising type. So, you know, Ising model is the plane model with vertices, in vertices seat spins, and you have hexagonal, triangle, or quadratic lattice. They are both all equivalent 3. And the same is here. So this star triangle relation is exactly the elliptic beta integral. You can rewrite it in this way. Chi is just normalization constant. Here is a functional form. This is precisely the 100% accurately written elliptic beta integral with some normalization constant given here. And so Bajan Sergeyev in 2010 suggested the model of the generalizing all known Ising type models with the Boltzmann phase given by these combinations of elliptic gamma functions and the star triangle relation, which I have found long ago, and suggested them and solved essentially. They have found this free energy per edge in the asymptotic limit, in the thermodynamic limit. And so it's a very nice working model. And my point is that if you look for the lattice models, you can continue hexagonal lattice, triangle lattice, whatever, and ask what kind of field theory model, four-dimensional field theory corresponds to such lattice models. It's called Quiver field theories. And what we have here gauge groups sitting in the vertices, and these are Boltzmann weights. These are given by this combination of elliptic gamma functions. And so four-dimensional Seiberg duality works here as the integrability condition. Seiberg duality is exactly the integrability condition. Star triangle relation is the Seiberg duality for the simplest n equal 1 4-dimensional quantum field theory, supersymmetric quantum field theory. And it goes, you can go further on, more general star-star relations instead of star triangle. Then it goes to V function symmetry and goes to IRS type I1 master, and so on and so forth. So essentially, what I'm coming to my beginning of my talk, we have a very deep relation between two-dimensional field theories, two-dimensional integrable models of statistical mechanics, and four-dimensional quantum field theory. In the topological sector of four-dimensional supersymmetric field theories, we sit essentially on the integrable models of two-dimensional type, of two-dimensional models. And through these superconformal indices and elliptic hypergeometric integrals, which I was working on. So thank you for your attention, and more congratulations to the—
Thank you.
You have, it seems that for PPS states, you know spectrum just from supersymmetry algebra. Because Hamiltonian eigenvalues.
What's this question?
Is it right?
Yes, it's true. You know this algebra. From that, you can classify the representations of these BPS states, long or short, and the superconformal index, exactly the generating function of the quantum numbers for these BPS states. This is generating function for those BPS states with all quantum numbers taken into account.
I have a question. So, do I understand correctly that these indexes you are talking about are some functions of some parameters, right? So they are not integer numbers.
That's true. They are analytical functions.
Analytical functions, but not integer numbers. So they have nothing to do with Witten index, for example.
They have very much to do with Witten index because if you wish, you can send all this, take special values for these complex parameters, and you will come to numbers. It's
integer numbers, so you can find the values of parameters such that you.
In principle, yes, it's an extension of Witten index, exactly through the addition of this analytical.
That I don't understand, because Witten index is related to Atiyah-Zinger index,
yes,
right? And Atiyah-Zinger index is always integer; it's not a function of anything. It's if you have functions,
this is character valued index. This is a character valued index. You see, these exponentials of the generators, they of course kill the integer of character. But if you look for the expansion of these indices into the series, say with respect to the P and Q, which are small parameters, then you will get sum of characters with integer coefficients in front of them. That's exactly the topological objects which you want.
So you are saying that these functions which you write are equivalent to a set, infinite set of integer numbers, right?
Yes, yes.
So it's the infinite set of Witten indices, right?
Yes, if you wish. Like character value. That's
now, can you give us some examples, some simplest theory? What is your index? What is the relation to Witten indices?
No, I didn't work on that. It's not my business in a sense. And, but people, of course, discuss these numbers in this community on quantum field theory and supersymmetric theory. That's and moreover, there are abstract mathematical theories where the cohomology spaces for this, you see, the q square equals to 0. You essentially look for quotients with respect to space to 0 modes, and that will be exactly the earlier characteristics for this very complicated non-commutative geometry described by these objects.
Then just an infinite series of infinite series of some manifolds then, right?
Yes.
Well, okay, so I will ask you for...
There is a question from Zoom.
Yes, Slava,
yes.
My question has been raised by other people, but I want to put it to you in a very concrete way. When I talk to someone like Claude Dor or Johannes Blumlein or Lorenzo Tancredi about their multiple elliptic integrals, they tell me where they are in the upper half of the complex plane. They tell me they've got a known Q exponential of 2 pi r tau. They tell me where they are, and that's fixed by some external continuous kinematic variable, right? Now you've got all of that machinery in your elliptic hypergeometric functions, but you can't tell me where you are on the complex plane. What is the physical significance of your continuous variables? Forget about the integer valued ones. People have asked you, what is the physics of that continuous variable?
Thank you for the question. One interpretation I gave already. So this, let's take this V function, then it becomes the eigenfunction of the very nice Hamiltonian. And so then, you know, of course, interpretation of these variables. These are parameters of your Hamiltonian, they describe potential. And so for self-adjointness, you choose particular restrictions. So that's clear. In the context of this superconformal indices, it's less clear. And actually, people use the formal approach without caring anything about the mathematically rigorous definition, and that imposes certain restrictions. For instance, P and Q modulus less than 1 is just the condition of convergence of all these integrals and functions. And I cannot dig out from my mind immediately the answer to your question, what will be the physical interpretation, but there is some. There is some, yes. Sorry for not being able to answer right away. But at least one I gave you.
Okay, thank you. So any more questions or comments? You have some?
No.
Okay, then we should finish our evening.